Hello there, and welcome back. Tonight we're going to drift through some of the most remarkable discoveries made by the James Webb Space Telescope, a machine we built to see what human eyes could never glimpse, to peer back through time itself, to witness the universe when it was young and strange and still learning how to be. These aren't just discoveries about distant light and ancient galaxies. They're glimpses into our own origins, traced backward through billions of years, written in wavelengths our eyes can't see, but our instruments can translate into wonder. Before we begin, I'd love to know where you are watching from tonight, and how was your day? Drop a comment below. I always enjoy reading your comments. If you enjoy falling asleep to these videos, please consider liking and subscribing. It helps more people find their way here. Now let's begin. There are some mysteries in astronomy that have troubled scientists for decades. Puzzles that seem to violate what we think we know about how cosmic structures form and evolve. One of the most persistent is the problem of supermassive black holes in the early universe, specifically how they got so massive so quickly. Black holes are strange objects, regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. They're predicted by general relativity, Einstein's theory of gravity, and we have overwhelming observational evidence that they exist. We've detected gravitational waves from black hole mergers. We've imaged the shadows of black holes using the Event Horizon Telescope. We've watched stars orbiting around what must be a supermassive black hole at the center of our galaxy. Black holes are real, well established, no longer controversial. But understanding how they form, especially how supermassive black holes form, has been challenging. Stellar mass black holes, those with masses between roughly 3 and 100 times the Sun's mass, form from the deaths of massive stars. When a massive star exhausts its nuclear fuel, its core collapses catastrophically, and if the core is massive enough, the collapse continues past the neutron star stage and forms a black hole. This process is well understood, consistent with our knowledge of stellar evolution, and observed regularly in the form of core collapse supernovae. But supermassive black holes, those with masses of millions or billions of times the Sun's mass, can't form directly from single stars. There's no star massive enough to collapse into a billion solar mass black hole. So supermassive black holes must grow over time, starting from smaller seeds and gradually accumulating mass through accretion of gas and mergers with other black holes. The problem is time. Growing a black hole from stellar mass seeds, tens of solar masses, to supermassive scales, millions or billions of solar masses, takes time, even under the most optimistic assumptions about accretion rates. Black holes can only accrete gas so fast. There's a physical limit called the Eddington limit, beyond which the radiation pressure from the infalling material becomes so intense that it blows away additional material before it can fall in. Accreting at the Eddington limit, a stellar mass black hole might double its mass every few tens of millions of years. Do the math, and you find that growing from a 30 solar mass seed to a billion solar mass supermassive black hole, even at the Eddington limit, takes about 1 billion years. That's fine if you have 1 billion years available. But Webb has observed supermassive black holes existing less than 700 million years after the Big Bang, in quasars that are already massive and luminous. already consuming vast amounts of gas, already billions of solar masses. The timeline doesn't work. There isn't enough time to grow from stellar mass seeds to supermassive black holes through continuous accretion, even under optimistic assumptions. So either black hole growth must somehow exceed the Eddington limit, perhaps through super Eddington accretion in specific conditions, or the seeds must be more massive than we thought, starting not at tens of solar masses, but at thousands or millions of solar masses. And that's where direct collapse black holes come in. The idea, proposed by theorists decades ago, is that under specific conditions in the early universe, massive clouds of gas might collapse directly into black holes without first forming stars. Normally, when gas clouds collapse, they fragment into smaller pieces that become individual stars. But if you can prevent fragmentation, if you can keep the cloud from cooling too much, keep it from forming molecular hydrogen that would radiate energy and allow further collapse, then the entire cloud might collapse as a single unit, forming a black hole with thousands or even millions of solar masses right from the start. These massive seeds could then grow to supermassive scales much more quickly, solving the timeline problem and explaining how we see billion solar mass black holes so early in cosmic history. Direct collapse black holes have been theoretically predicted for years, but they've never been definitively observed until possibly now, with Webb's discovery in August 2025 of what might be the first direct observation of this process. The object in question is in the Infinity Galaxy, existing in the very early universe, and Webb's observations suggest it might be witnessing a supermassive black hole forming via direct collapse. Gas collapsing directly into a million solar mass black hole without first forming stars. If confirmed, this would be the first direct observation of direct collapse, providing crucial evidence for a formation mechanism that's been debated for decades. The evidence comes from the spectrum. When astronomers analyzed the light from this object, they found signatures consistent with a massive black hole accreting gas, broad emission lines from material swirling at tremendous velocities, X-ray emission from hot gas near the event horizon, other markers of active black hole growth. But they didn't find the signatures of stars, at least not in the quantities you'd expect if this were a normal galaxy containing a supermassive black hole. In normal galaxies, even active galaxies with bright central black holes, there's always a surrounding stellar population, billions of stars that formed over time from the same gas reservoirs that fed the black hole. The stars and the black hole grow together, co-evolving, influencing each other's development. But in this object, the stellar component seems absent or extremely weak, suggesting a black hole that formed without an accompanying stellar population, or at least that formed before significant star formation occurred. This is consistent with direct collapse. In the direct collapse scenario, a massive gas cloud collapses quickly before star formation can proceed, creating a black hole seed that then begins accreting additional material. Star formation might occur later once conditions change, but initially you'd have a black hole without the expected stellar environment. Exactly what Webb seems to have observed. But confirmation is difficult. Proving that this is genuinely direct collapse and not some other phenomenon requires detailed observations, careful analysis, consideration of alternative explanations. Maybe it's a heavily dust-obscured galaxy where the stars are hidden behind thick dust clouds that absorb their light. Maybe it's an unusual viewing angle or a transient phenomenon or some quirk of the system's evolution that makes it appear different from normal galaxies. Astronomers are cautious about claiming discoveries, especially discoveries of processes that have been predicted but never observed. It takes time to rule out alternatives, to gather additional data, to convince the community that the interpretation is correct. So the discovery is tentative, preliminary, awaiting confirmation through additional observations and analysis. But if it holds up, if this really is direct collapse in action, it would solve multiple problems at once. It would explain how supermassive black holes grew so massive so quickly in the early universe. It would provide the first direct observation of a formation mechanism that's been theoretically necessary, but observationally elusive. It would validate decades of theoretical work predicting that direct collapse should occur under specific conditions in primordial gas clouds. And it would add another chapter to the remarkable story of how the universe builds its structures, how it transforms simple initial conditions, hydrogen and helium gas, slight density fluctuations, the fundamental forces of physics, into the rich complexity we observe today. Direct collapse would be another example of nature finding multiple pathways to the same result, multiple mechanisms for building supermassive black holes depending on conditions and circumstances. The universe is remarkably creative in this way, exploring different solutions to the problem of structure formation. Galaxies form through hierarchical merging of smaller systems. Stars form through gravitational collapse of molecular clouds. Planets form through accretion in circumstellar disks. Black holes form through stellar collapse, through mergers, and possibly through direct collapse. Nature doesn't rely on a single mechanism. It uses whatever works given the local conditions, whatever pathways are available given the physics and chemistry and dynamics of the situation. This multiplicity of mechanisms makes the universe more complex, but also more robust. If one pathway is blocked, if conditions don't allow one formation mechanism, other pathways might still work, ensuring that structures form even when conditions aren't ideal. It's redundancy built into physics, multiple routes to complexity, ensuring that the universe can build its structures under a wide range of circumstances. Direct collapse black holes, if they exist, represent one such alternative pathway, a way to build massive black hole seeds quickly when conditions prevent the normal pathway through stellar evolution. They're not common in the modern universe, where metallicity is higher and gas can cool more efficiently, allowing star formation to occur before direct collapse can proceed. But in the early universe, with its pristine gas composition and specific conditions, direct collapse might have been relatively common, providing the massive seeds necessary to build the supermassive black holes we observe in early quasars. And there's something almost elegant about the idea, don't you think? That nature found a way to build massive black holes quickly when the universe needed them. That the physics worked out just right to allow direct collapse in the specific conditions of cosmic dawn. That the universe had a mechanism ready for building the structures it required. It's not intentional, of course. Physics doesn't have foresight, doesn't plan ahead, doesn't engineer solutions. But the laws of physics, operating across vast timescales and enormous systems, naturally produce the structures we observe, naturally build the complexity we see, naturally transform initial conditions into rich, structured outcomes. And sometimes the mechanisms that emerge from those laws seem almost too perfect, too well suited to the requirements, to be merely accidental. But they are accidental, in the sense that they're not designed. They're simply what happens when matter and energy interact under the constraints of physical law, when gravity and thermodynamics and quantum mechanics and relativity all work together, when billions of years of evolution and countless interactions compound into the cosmic structures we observe today. Direct collapse black holes, if confirmed, would be one more example of physics doing what physics does, creating structure, building complexity, transforming simple initial states into rich, varied outcomes. And the fact that we might be witnessing this process, observing it happening in the early universe through Webb's infrared vision, is a testament to how far our observational capabilities have advanced, how much we can learn about cosmic processes from careful analysis of ancient light. Rest now, knowing that the universe has mechanisms for building its structures, pathways from simplicity to complexity, processes that operate over billions of years to create the cosmic landscape we observe. Direct collapse black holes, if they exist, are one such mechanism. Nature's solution to the problem of building massive black holes quickly. A pathway available in the specific conditions of the early universe, contributing to the rich diversity of cosmic phenomena we're learning to understand and appreciate. The universe builds, relentlessly and patiently, using whatever mechanisms physics provides, creating structure from initial conditions, transforming energy into matter, into organized systems, into the vast cosmic web we inhabit. If you could step outside of time for a moment, become a cosmic observer watching the universe unfold at whatever speed you chose, you might choose to watch the birth of stars. It's one of the most fundamental processes in the universe, the mechanism by which gravity transforms diffuse clouds of gas into the brilliant fusion engines that light up the darkness and forge the elements that make complex chemistry and eventually life possible. But there's a problem with watching stars being born. They're hidden. They form deep inside enormous clouds of gas and dust, wrapped in cosmic nurseries so thick and opaque that visible light can't escape. For most of human history, we could only see the results, the bright young stars that had already emerged, already cleared away their birth cocoons, already announced their presence to the universe with brilliant light. The actual moment of birth, the ignition point, where gravity's patient compression finally triggers nuclear fusion, remained hidden from our eyes. Until now, until Webb. Among the very first science images released by the James Webb Space Telescope in July 2022 was a view of the Carina Nebula that astronomers immediately nicknamed the Cosmic Cliffs. And the name is apt. The image shows what appears to be a towering mountain range, peaks and valleys sculpted in golden and orange hues, rising against a deep blue background studded with stars. It looks almost terrestrial, almost like a landscape you could hike through, if it weren't for the impossible scale and the stars scattered throughout the scene. But it's not a solid surface. It's a boundary, the edge of an enormous cavity carved out by intense radiation and stellar winds from massive young stars outside the frame. The mountains are walls of gas and dust being eroded, eaten away by starlight, their surfaces glowing and heating under the relentless pressure of photons. And there, hidden in those walls, revealed for the first time by Webb's infrared vision, are hundreds of previously invisible newborn stars. The nebula itself, NGC 3324, lies about 7,600 light-years away in the direction of the constellation Carina. That's relatively close by cosmic standards, still within our own galaxy, the Milky Way, though far enough away that the light we're seeing left during the Bronze Age, when humans were just beginning to write down their stories and laws, when the pyramids were already ancient. But the stars Webb revealed in that image, those golden jets shooting out from newly formed stellar infants, those bright spots emerging from the dust, they're witnessing stellar birth happening right now. Or at least right now, as measured from our frame of reference, accounting for the time it takes light to reach us. The process we're watching, the transformation from dark cloud to brilliant star, takes somewhere between 50,000 and 100,000 years per star. That might seem long by human measures. It's longer than our species has had written language, longer than we've had agriculture. But in cosmic terms, it's barely a moment, a blink, an instant. Stars spend millions or billions of years in their stable, adult phase, patiently fusing hydrogen into helium, generating the energy that makes them shine. But their birth is quick and violent by comparison. A rapid collapse followed by the sudden ignition of fusion, followed by the equally rapid dispersal of the cloud that surrounded them. We're watching that brief window, that cosmic instant when gravity's patient work suddenly pays off and a new source of light switches on in the universe. And those jets, those golden streams of material shooting out perpendicular to the forming star's disk, they're particularly fascinating. They're one of the signature features of stellar birth, matter being funneled along magnetic field lines and ejected at tremendous speeds, carrying away excess angular momentum and allowing the central star to continue accreting mass without spinning itself apart. They're the exhaust ports of creation, the stellar equivalent of a newborn's first cry. What's remarkable is that this process, which we're seeing in the Carina Nebula 7,600 light-years away, is the same process that formed our own sun 4.6 billion years ago. Somewhere in a long-vanished molecular cloud, gravity began pulling material together. The center got denser and hotter, eventually igniting fusion, and jets of material shot out perpendicular to the forming solar system's disk. Our sun was once a bright spot in some ancient nebula's wall of gas, invisible to any observer except in infrared. A newborn star taking its first steps into a lifespan that will last about 10 billion years. And planets form in those disks, the flattened collections of gas and dust that rotate around the young star. In the Carina image, we can't see the disks directly, but we know they're there, hidden in the glowing dust around each protostar. And in those disks, the same processes that built Earth and Jupiter and all the other worlds of our solar system are happening again. Billions of dust grains sticking together, forming pebbles, forming boulders, eventually forming planetesimals and protoplanets, and given enough time, full-fledged worlds. It's a bit overwhelming when you think about it, that the universe is constantly, persistently, relentlessly making new stars, new potential solar systems, new chances for planets to form and evolve, and maybe, someday, develop life. The Carina Nebula alone is forming thousands of stars, And Carina is just one stellar nursery among thousands in our galaxy. And our galaxy is one among hundreds of billions in the observable universe. Starbirth isn't rare. It's not a special event. It's a fundamental, ongoing process, as natural to the universe as waves are to an ocean. The universe makes stars the way trees make leaves, constantly, prolifically, without apparent effort. And each star is a new opportunity for complexity, a new forge for elements, a new source of light pushing back against the darkness. There's something deeply comforting about that, I think. The universe isn't done. It's not winding down just yet. It's still actively creating, still forming new structures, still exploring the possibility space of what matter can do when gravity brings it together and nuclear fusion lights it up. We live in a universe that's in its prime creative phase, busily making stars that will burn for billions of years, planets that will orbit for trillions. So when you look at the cosmic cliffs, you're not just seeing a pretty picture, though it is achingly beautiful, with those golden hues and that deep cosmic blue. You're seeing Genesis. You're seeing the process that made the sun that warms your face, the star that made the earth possible, the fusion engine that gives our solar system its heartbeat. You're seeing your own origin story written in gas and dust and light. And maybe that's enough to contemplate for now. Maybe it's enough to know that somewhere out there, 7,600 light years away, stars are being born right this moment, beginning their long journeys through the cosmos, journeys that might last longer than our species will exist. The universe is taking care of its own continuity, making new stars to replace the old ones that burn out, maintaining the great cycle of stellar birth and death that keeps galaxies alive and shining. Rest easy in that knowledge. The cosmos is doing its work. New stars are igniting even as you close your eyes. Time is a strange thing to think about when you're trying to sleep. Maybe you're thinking about tomorrow, or replaying today, or remembering something from years ago. But those time scales, hours, days, years, they're the time scales we're built for, the ones our brains evolved to handle. What we're not built for is deep time, cosmic time, the kind of time where 1,000,000 years is a brief interval, and 1,000,000,000 years is just getting started. And yet, that's exactly where the James Webb Space Telescope takes us. Within its first year of operation, Webb discovered and spectroscopically confirmed over 20 galaxies that formed in just the first 400 to 600 million years after the Big Bang. Let me say that again, more slowly. Galaxies that existed when the universe was less than 500 million years old, in a cosmos that's currently 13.8 billion years old. These galaxies were formed and shining when the universe was between 3 and 4% of its current age. To put that in perspective, if the universe were a person, these galaxies would be the equivalent of memories from before that person learned to walk, before they could form sentences, from the earliest possible moments of consciousness. And yet there they are, captured by Webb's instruments, not as vague smudges or uncertain signals, but as spectroscopically confirmed objects with measured redshifts and calculated distances, and real, meaningful data about their composition and properties. Spectroscopy is how we know these galaxies are real, and not just noise or nearby objects masquerading as distant ones. When you spread light out into its component wavelengths, like a prism spreading sunlight into a rainbow, You can see dark lines or bright lines at specific wavelengths, created by atoms absorbing or emitting light. Those lines are like fingerprints. Each element creates its own unique pattern. Hydrogen makes certain lines. Oxygen makes others. Carbon, nitrogen, iron. Each leaves its signature in the spectrum. But here's the clever part. As the universe expands, it stretches space itself, and that stretching pulls on the light traveling through it, shifting all those spectral lines toward longer wavelengths, toward the red end of the spectrum, hence redshift. The farther away something is, the more space has expanded during the light's journey, and the more redshifted those spectral lines become. So by measuring exactly where those hydrogen lines appear, how far they've shifted from their normal positions, we can calculate the distance to the galaxy and therefore how long ago the light was emitted. And these galaxies, they're spectroscopically confirmed to be from the first few 100 million years of cosmic history. They're time capsules, showing us what the universe looked like when it was still in its infancy, still figuring out how to organize matter into large-scale structures. The early universe wasn't like today's universe. Right after the Big Bang, for the first 380,000 years or so, the cosmos was so hot and dense that atoms couldn't form. Electrons and protons existed separately, creating a kind of foggy plasma that scattered light constantly. This was the cosmic fog, and it made the universe opaque. Light couldn't travel freely because it kept bouncing off free electrons. But then, as expansion cooled things down, atoms finally formed. Protons and electrons combined to make neutral hydrogen, and suddenly the universe became transparent. Light could travel freely. This moment is called recombination, and the light from that era is what we now see as the cosmic microwave background radiation, the afterglow of the Big Bang. After recombination came the cosmic dark ages, a period of several 100 million years when the universe was mostly just neutral hydrogen gas. No stars, no galaxies, just vast clouds of simple atoms slowly collapsing under gravity's patient pull. It was dark, not because light was trapped, but because there were no sources of light. The cosmic microwave background had already cooled and redshifted into invisibility, and stars hadn't formed yet to illuminate the void. Then gradually, gravity won. The densest regions of gas collapsed enough to form the first stars, not in galaxies at first, just isolated stars or small clusters, population 3 stars made of pure hydrogen and helium, massive and short-lived, burning bright and fast. Those first stars started producing heavier elements, started reionizing the hydrogen around them, splitting it back into protons and electrons with their intense ultraviolet radiation, and started the process of ending the dark ages. And then came the first galaxies, collections of millions of stars bound together by gravity, manufacturing elements, producing light, organizing the universe into recognizable structures. This period, from the formation of the first stars to the complete reionization of the universe, is called the cosmic dawn, or the epoch of reionization, and it lasted roughly from 100 million to about 700 million years after the Big Bang. And Webb is showing us galaxies from right in the middle of that era. We're witnessing cosmic dawn itself, seeing the universe's first large-scale structures forming, watching the moment when darkness gave way to light on the largest possible scale. These aren't just blobs of light to astronomers. They're readable documents, scrolls written in photons. The spectra tell us what elements are present, how fast the galaxies are moving, how much star formation is happening, what the temperature is, how massive they are. Each galaxy is a data point, a measurement, a constraint on our models of how the early universe worked. And what's fascinating, what keeps astronomers awake at night, though hopefully you're drifting off, is that these early galaxies are surprisingly sophisticated. They shouldn't be, according to the models that worked so well for later cosmic history. Galaxies should have formed slowly, gradually, building up mass over hundreds of millions of years. But some of these earliest galaxies are already massive, already enriched with heavier elements, already showing signs of organized structure. It's as if the universe learned to make galaxies quickly, like a master craftsperson who immediately produces mature work without a long apprenticeship. And that means our models need adjustment. It means the early universe was perhaps more efficient at converting gas into stars, more effective at gathering matter into gravitationally bound structures than we expected. But that's how science works, isn't it? We build models based on what we can observe, and then we build better instruments and observe more. And sometimes, often, we discover that reality is more interesting, more surprising, more complex than we thought. The universe doesn't care about our theories. It does what it does. Following physical laws we're still learning to fully articulate, and our job is to update our understanding to match what we actually see rather than what we expected to see. These ancient galaxies from cosmic dawn are teaching us that the universe was precocious, forming structures early and efficiently. They're showing us that galaxy formation in the early universe wasn't a slow, hesitant process, but a vigorous, productive one. They're revealing a cosmos that knew what it was doing from remarkably early on, assembling the building blocks of structure, stars, galaxies, eventually clusters of galaxies, with surprising speed and sophistication. And somewhere in that early universe, in one of those ancient galaxies, were the raw materials that would eventually, billions of years later, through countless cycles of stellar birth and death, through the formation of new generations of stars from the enriched remnants of old ones, become the matter that makes up our solar system, our planet, our bodies. Every atom in you except hydrogen was made in stars. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all forged in stellar cores and scattered through space by supernovae, to be gathered up into new clouds, new stars, new planets. And that process started in those earliest galaxies, those first collections of stars manufacturing the first batches of heavy elements, seeding the cosmos with the periodic table, making chemistry possible, making planets possible, making life possible. So those distant ancient galaxies aren't just abstract objects in the far reaches of space and time. They're your ancestors, in a very real sense. They're the beginning of the chain of cosmic events that led to you existing, here, now, listening to a voice talk about photons captured by a telescope 1,000,000 miles from Earth. It's a long chain, spanning billions of years and unimaginable distances. But it's unbroken. It's continuous. You are the universe looking at itself, made possible by those first galaxies lighting up in the cosmic dawn, starting the great project of building complexity from simplicity, structure from chaos. And maybe that's enough for tonight. Maybe it's enough to know that you're connected through time and space and stellar processes to the very earliest moments when the universe first began to shine. Close your eyes now. The ancient galaxies are still there, still shining, patiently waiting to tell us more of their secrets. They've waited 13 billion years. They can wait until morning. There are record holders in every field, aren't there? The tallest building, the fastest runner, the oldest tree. We seem to have a natural fascination with extremes, with pushing boundaries, with finding the edge of what's possible. And in astronomy, one of the most sought-after records is the most distant object, the farthest thing we can see, the oldest light we can capture, the deepest look back into time that our instruments can achieve. For years, that record kept changing as telescopes improved and techniques advanced. Each new record holder would reign for a while, sometimes years, sometimes just months, before being dethroned by an even more distant object. And then James Webb arrived, and the record started falling with remarkable frequency. Because Webb was built for this, designed specifically to see the earliest galaxies, equipped with infrared sensors that could detect light that had been stretched by cosmic expansion into wavelengths invisible to human eyes. And in May 2024, astronomers announced a new record holder, JWST GS-Z140. The name is technical, almost industrial. JWST stands for the JWST Advanced Deep Extragalactic Survey, and the rest is catalog notation. But what it represents is anything but mundane. This galaxy exists, or rather, existed, just 290 million years after the Big Bang, appearing to us with a redshift of 1432. Let me unpack what that means, because 290 million years after the Big Bang sounds like a long time, until you remember that the universe is 13.8 billion years old. This galaxy formed when the universe was only about 2.1% of its current age. If the universe's history were compressed into a single year, this galaxy would have formed around January 8th. We're seeing it at the very beginning of cosmic history, in those first formative moments when the universe was still experimenting with how to build large structures. The redshift of 14.32 is extraordinary. Remember, redshift measures how much the universe has expanded since the light was emitted. A redshift of 14.32 means the universe has expanded by a factor of 15.32 since that light began its journey. The wavelengths of light have been stretched by that same factor. What was once ultraviolet light, when it left the galaxy, has been pulled and stretched into infrared by the time it reaches Webb's mirrors. But here's what makes JWST GS-Z140 truly puzzling, truly remarkable, truly worthy of keeping astronomers up at night while you're drifting off. It shouldn't be as massive and luminous as it is, not that early, not according to our best models of how galaxies form and grow. The galaxy contains several 100 million solar masses of stars. That's several 100 million times the mass of our sun, all gathered together, all formed from gas in just 290 million years. And it's luminous, bright enough to be detected across 13.5 billion light-years of expanding space. And it's extended, spanning about 1,600 light-years across, which might not sound like much compared to the Milky Way's 100,000 light-year diameter, but for such an early galaxy, it represents significant structure and organization. The problem, or rather the fascinating puzzle, is that building something this massive and organized should take longer than 290 million years, according to the physics we understand. Star formation isn't instantaneous. Gas clouds have to collapse under gravity, which takes time. Stars have to form, live, and die, enriching the gas with heavier elements, which takes more time. Multiple generations of stars need to cycle through their lives to produce the kind of complex chemistry we see in this galaxy's spectrum. And all of that is supposed to be a gradual process, accumulating mass and complexity over hundreds of millions of years. But here's JD's GS Z40, already mature and massive when the universe was barely out of its infancy, already shining brightly, already organized into a structure we can recognize as a galaxy, rather than just a chaotic collection of protostars. It's as if nature had perfected the recipe immediately, skipping the expected learning curve and producing sophisticated results from the very beginning. Several theories attempt to explain this. Maybe the early universe was more efficient at converting gas into stars than the later universe. Perhaps the conditions in those first few 100 million years allowed for more rapid star formation, higher efficiencies, faster processes. Maybe dark matter, that mysterious substance that makes up most of the matter in the universe, was distributed in ways that enhanced early galaxy formation, creating deeper gravitational wells that could gather and condense gas more quickly. Or maybe, and this is where it gets really interesting, maybe supermassive black holes formed earlier than we thought, and their presence in the centers of these young galaxies somehow enhanced star formation around them, creating a kind of feedback loop where the black hole's activity triggered bursts of rapid star formation in the surrounding gas. We know that black holes and galaxies evolved together, influencing each other's growth. But we're still working out the details of exactly how that relationship works, especially in the early universe. Or perhaps our models of the early universe need more fundamental revision. Perhaps the density fluctuations left over from the Big Bang, those slight variations in density that eventually grew into all the structure we see today, were stronger or more concentrated than we thought in certain regions. Perhaps the cosmic dark ages weren't quite as uniform as we imagined, with pockets of enhanced star formation beginning earlier than our standard timeline suggests. Whatever the explanation turns out to be, JD's GS Z14-0 is telling us something important about the early universe. It's a data point that doesn't quite fit the smooth curves of our models, and those are often the most valuable data points, the ones that force us to refine our understanding, to add nuance and complexity to what might have been oversimplified theories. And there's something almost poignant about this galaxy, isn't there? It existed for perhaps a few 100 million years in the early universe, forming stars, building structure, shining its light out into the expanding cosmos. And then, as the universe continued to evolve, it likely merged with other galaxies. That's what small galaxies do in the early universe. They combine and combine, gradually building up into the large galaxies we see today. So JDA's GS Z0 doesn't exist anymore, not as a separate entity. It's probably now part of some massive galaxy in the modern universe. Its stars mingled with stars from dozens or hundreds of other ancient galaxies. Its identity lost in the mergers and collisions that built today's cosmic structures. But its light remains. That's the beautiful thing about the finite speed of light and the vastness of space. Even though the galaxy itself transformed long ago, merged and changed beyond recognition, The light it emitted 290 million years after the Big Bang is just now arriving at our telescopes. We're receiving a message sent 13.5 billion years ago, a postcard from the dawn of time, telling us that galaxies were already here, already shining, already building the foundations of the universe we inhabit today. And somewhere in that ancient galaxy, in the gas enriched by its first generations of stars, were atoms that might eventually, after countless more cycles of stellar birth and death, after innumerable cosmic events, have become part of our galaxy, our solar system, maybe even our own bodies. The universe recycles everything, and the atoms in you have been through many previous incarnations, previous stellar systems, previous galaxies. You are, quite literally, made of ancient starlight, forged in galaxies that no longer exist as separate entities, but whose contribution to the cosmic story continues in every atom of your being. Jada's GS Z140 is part of that story, one of the earliest chapters. A galaxy from the dawn of cosmic history, contributing its small but significant part to the great chain of causation that leads, improbably, to consciousness arising and looking back at its own origins. It's a humbling thought, in the best possible way. Not humbling in the sense of making you feel small or insignificant, but humbling in the sense of placing you in context, showing you the immense journey that led to this moment. The billions of years of cosmic evolution required to transform a hot, dense early universe into one that contains galaxies and stars and planets and life and minds capable of understanding their own origins. So rest now, knowing that you're the product of 13.8 billion years of cosmic effort, of stars forming and dying, of galaxies colliding and merging, of chemistry and physics working together to build complexity from simplicity. You're not separate from the universe. You're an intrinsic part of it. The universe exploring itself, examining its own history, marveling at its own improbable journey from that first brilliant moment to this quiet one. Here, now, as you close your eyes and drift toward sleep. The most distant galaxy we've ever seen is still there, in a sense, its light continuing to spread through space, perhaps eventually reaching alien eyes on worlds we'll never know about, telling them the same story it's telling us, that the universe began in brilliance and has been creating ever since, building and building, never stopping, never resting, until somehow, impossibly, it built beings capable of looking back and understanding where they came from. There's something deeply satisfying about symmetry, isn't there? The human brain seems wired to find beauty in balanced forms, in patterns that repeat, in structures that mirror themselves. Maybe it's because symmetry often signals something fundamental about the underlying physics, some conservation law or geometric necessity that nature can't avoid. Or maybe we just find it aesthetically pleasing, a sense of rightness when things balance out. Whatever the reason, the image of protostar L1527 that Webb captured strikes that deep chord of symmetry. It shows an hourglass, a perfect glowing hourglass suspended against the black of space, with a dark band cutting horizontally across its narrow center. The upper and lower lobes glow in different colors, the upper portion in shades of blue and the lower in orange and red, creating a gradient that looks almost painted, almost too perfect to be real. But it is real, deeply, fundamentally real. What you're looking at is a star being born right now, or at least right now, as measured from 430 light years away, accounting for the time it takes light to reach us. The protostar L1527 is only about 100,000 years old, which in stellar terms makes it a newborn, barely a moment old. Our Sun is 4.6 billion years old, a mature, middle-aged star that's been steadily fusing hydrogen for longer than Earth has existed. L1527 hasn't even begun its main sequence life yet. It's still in the process of forming, still gathering mass, still contracting under gravity, still heating up toward the temperature where nuclear fusion can ignite. The hourglass shape isn't the star itself. The protostar is hidden in that dark band across the middle, shrouded in a thick disk of dust and gas that blocks even Webb's infrared vision. What we're seeing is the cavity the young star has carved out in the surrounding molecular cloud, a space cleared by the star's stellar winds and outflows. The star is blasting material outward in jets perpendicular to its disk, and those jets are plowing into the surrounding gas, heating it, pushing it aside, creating these beautiful glowing lobes that extend outward in opposite directions. The color difference between the upper and lower lobes tells us about the environment. The blue regions represent areas where the dust is thinnest, allowing shorter wavelengths of light to pass through and be detected by Webb's near-infrared instruments. The orange and red regions are where the dust is thicker, filtering out the blue light and leaving only the longer wavelengths to emerge. It's the same physics that makes sunsets red. Longer wavelengths penetrate dust better than shorter ones, but on a cosmic scale. And that dark band, that's the disk. The protoplanetary disk, to be specific, though at this early stage it's really a protostellar disk, still feeding material onto the star, still contributing to the star's growth. The disk is edge-on from our perspective, so we're looking directly at its plane, and it's so thick with dust that not even infrared light can penetrate it. Somewhere in that disk, embedded in the darkness, is the protostar itself, a warm, dense core maybe half the mass of the Sun, slowly contracting, slowly heating, not yet hot enough to fuse hydrogen, but getting there, getting closer with each passing 1,000 years. In a few 100,000 more years, maybe less, maybe more, stellar formation timelines are fuzzy. That core will reach about 10 million degrees Kelvin in its center, and hydrogen fusion will ignite. That's the moment of stellar birth, the transition from protostar to star, the point where the object stops contracting and reaches hydrostatic equilibrium, where the outward pressure from fusion energy balances the inward pull of gravity. At that moment, L1527 will become a main sequence star, a proper member of the stellar community, beginning a stable life that will last billions of years. But even after fusion ignites, the disk won't immediately disappear. It will linger for several more million years, gradually dissipating, gradually being consumed by the star or blown away by stellar winds, or, crucially, gradually coalescing into planets. And that's where the story becomes personal, in a sense. That's where L1527 connects to us directly. Because 4.6 billion years ago, our Sun looked like this. Not exactly like this. Every protostellar system has its own characteristics, its own mass distribution, its own specific conditions. But the essential process was the same. There was a molecular cloud, a region of space filled with gas and dust, mostly hydrogen with traces of heavier elements forged in previous generations of stars. Something disturbed that cloud, maybe a nearby supernova shockwave, maybe a collision with another cloud, maybe just spontaneous gravitational instability. The cloud began to collapse, spinning faster as it contracted, like a figure skater pulling in their arms. Conservation of angular momentum, demanding that rotation speed up as size decreases. The center became denser and hotter, forming a protostar. Material that couldn't fall directly into the center. Material with too much angular momentum settled into a disk around the equator. The protostar began blasting out jets of material along its rotation axis, clearing cavities in the surrounding cloud, creating an hourglass glow just like L1527's. And in that disk, over millions of years, dust grains stuck together, forming pebbles, forming boulders, forming planetesimals, eventually forming the planets we know today. Mercury, Venus, Earth, Mars, the gas giants, the ice giants, all the asteroids and comets, everything in our solar system. So when you look at L1527, you're looking at your own past. You're seeing the process that made the solar system, the star formation event, that led eventually to Earth existing, to life arising, to consciousness developing, to you being here right now, contemplating photons that traveled 430 light years to tell you this story. And it's happening everywhere. Star formation isn't rare or unusual. It's a constant, ongoing process throughout galaxies. Right now, in the Milky Way alone, dozens of new stars are forming, maybe hundreds, each one creating its own disk, its own potential planetary system, its own future. Some of those stars will form planets. Some of those planets will be in the habitable zone, the right distance from their star where temperatures allow liquid water. Some of those might develop life, given the right chemistry and enough time. We don't know how common life is. That's one of the great unanswered questions, one of the mysteries that keeps scientists up at night. But we do know that the raw materials are common. Every star forms from essentially the same basic ingredients, and the heavy elements necessary for complex chemistry are being continuously manufactured and distributed by stellar processes. We know that planets are common. Almost every star we've examined closely seems to have planets, suggesting that planet formation is a natural byproduct of star formation, not a rare accident. And we know that chemistry is universal. The same physical laws, the same atomic interactions that allowed life to develop on Earth operate everywhere in the universe. So maybe, when we look at L1527's protoplanetary disk, we're not just seeing our past. Maybe we're also seeing someone else's future. Maybe in that disk, a few million years from now, planets will form. Maybe one of them will be rocky, the right distance from the star, with the right chemistry and the right conditions. Maybe, given billions of years, something will emerge there that looks up at its own sky, builds its own telescopes, discovers its own ancient galaxies, and wonders if it's alone. Or maybe not. Maybe we're unique, the only time in the history of the universe that matter has organized itself into consciousness. That would be remarkable too, in its own way. Equally humbling and equally profound. The idea that in all the vast cosmos, in all the countless stars and planets, we're it, the sole observers, the only eyes through which the universe can see itself. But either way, whether life is common or rare, whether consciousness is abundant or unique, the process of star formation continues. Indifferent to those philosophical questions, L1527 is forming whether or not its planets will harbor life. The hourglass glows, the jets flow, the disk rotates, gravity does its patient work, and eventually, inevitably, a new star will ignite, adding its light to the vast collection of stellar fires that make galaxies shine. There's a circularity to it all, isn't there? Stars form from clouds of gas enriched by previous stars. They fuse hydrogen into helium and heavier elements. They live for millions or billions of years. Eventually they die, some quietly, some violently, returning their enriched material to the interstellar medium. That material mixes with primordial hydrogen, forms new clouds, collapses into new protostars, makes new stellar hourglasses like L1527, starts the cycle again. Every atom of carbon, nitrogen, and oxygen in your body has been through that cycle multiple times. Those atoms were forged in stars that died before the sun formed, released into space, incorporated into the molecular cloud that became our solar system, eventually ending up in the disk of dust and gas that formed Earth, incorporated into minerals and water, cycled through geological processes, eventually taken up by living organisms, passed through ecosystems, and finally, improbably, impossibly, assembled into the specific arrangement that makes you a conscious being capable of understanding your own atomic history. So when you breathe, you're breathing atoms that were once in stars, forged in stellar cores, scattered through space, gathered together by gravity, incorporated into a planet, cycled through life, and now temporarily part of you before being returned to the environment to continue their journey. You're not just on Earth, you're made of Earth, and Earth is made of stardust, and stardust is made in stellar furnaces like the one L1527 will become once fusion ignites. The hourglass is beautiful not just aesthetically but conceptually. It represents transformation, the conversion of one thing into another, diffuse gas into concentrated star, potential energy into actual structure, simplicity into complexity, and it represents time in a sense, the hourglass measuring out the moments between now and the moment when L1527 becomes a proper star, begins its main sequence life, starts the long process of fusing elements and generating light. But unlike a sand hourglass that can be flipped and run again, stellar hourglasses run only once. Each star gets one life, one chance to shine, one opportunity to fuse its fuel and contribute its light to the universe. And when it's done, the configuration that made that particular star unique is gone forever, dispersed back into the cosmic mix, ready to become part of something new. So rest now, knowing that you're part of that grand cycle, that vast cosmic process of transformation and renewal. The hourglass of L1527 is glowing 430 light years away, counting down toward stellar ignition, and in a sense it's counting down toward all the possibilities that stars' existence will enable. Planets, perhaps life, perhaps consciousness, perhaps beings that will look up at their own sky and wonder about their own origins, just as we do. The universe makes stars the way the ocean makes waves, continuously, naturally, as an expression of its fundamental nature. And each star is a new beginning, a new opportunity for complexity, a new light pushing back the darkness. Close your eyes now. The hourglass glows on, patient and beautiful, marking time in the cosmos. Galaxies seem so permanent, don't they? When you look up at the night sky on a clear night, away from city lights, you can see the Milky Way stretching across the darkness. A band of diffuse light that represents our galaxy seen edge on from our position within it. It looks eternal, unchanging, as permanent as anything in the universe could be. But galaxies aren't static. They're dynamic, evolving, violent even. They collide, merge, tear at each other with tidal forces, spawn new generations of stars in the turbulence of their encounters. Our own Milky Way is currently in the slow-motion process of consuming several smaller satellite galaxies, and in a few billion years, it will collide with Andromeda, our nearest large galactic neighbor, creating a new, larger elliptical galaxy that astronomers have already nicknamed Milkomeda. But galaxy mergers aren't just a modern phenomenon, something that only happens in the mature universe. They've been happening since the very beginning, since the first galaxies formed. In fact, mergers are how large galaxies form. Small galaxies collide and combine, making medium galaxies, which collide and combine with others, gradually building up the massive galaxies we see today through billions of years of hierarchical assembly. And James Webb has captured the earliest galaxy merger ever observed, MAX 647 JD, existing just 300 to 500 million years after the Big Bang, beating the previous record by about 300 million years. What makes this observation remarkable isn't just the age, though that's certainly impressive. It's what the merger tells us about the early universe, about how quickly structure was forming, how dynamic and active those first few 100 million years really were. The galaxy appears as two distinct clumps in Webb's images, two separate concentrations of stars and gas, distinguished by their different colors in Webb's infrared vision. And they're close together, close enough that they're gravitationally bound, close enough that they're in the process of merging, spiraling together under their mutual gravitational attraction. Eventually, probably within a few 100 million years from when we're seeing them, they'll combine into a single, larger galaxy, their stars mingling, their gas mixing, triggering bursts of new star formation as the merger compresses gas clouds and initiates collapse. Galaxy mergers are spectacular events, though they happen in slow motion from our perspective because of the vast distances and timescales involved. When two galaxies collide, the stars themselves almost never actually hit each other. Space is mostly empty, and stars are tiny compared to the distances between them. If you scale the sun down to the size of a period on this page, the nearest star would be about 10 miles away. So even when two galaxies interpenetrate, their stars just pass by each other, like two swarms of bees passing through each other, mostly without collision. But the gas collides. Gas clouds are large and diffuse, and when two galaxies merge, their gas clouds slam into each other, shock heating, compressing, triggering enormous bursts of star formation. These are called starburst galaxies, and they can form stars at rates hundreds or thousands of times faster than normal galaxies. The Milky Way forms roughly 1 or 2 new stars per year, averaged over time. A starburst galaxy might form hundreds of stars per year, blazing through its gas supply in a cosmologically brief period, creating spectacular populations of hot, young blue stars. And the supermassive black holes at the centers of the galaxies, because essentially all galaxies have supermassive black holes at their centers, millions or billions of times the mass of the Sun. Those black holes eventually merge too, though that process takes even longer. First, they have to spiral down to the center of the combined galaxy, shedding orbital energy through gravitational interactions with surrounding stars. Then, when they're close enough, they begin to merge directly, finally coalescing in a burst of gravitational waves, ripples in space-time itself that propagate outward at the speed of light. We've detected gravitational waves from black hole mergers. That was one of the major discoveries of the 21st century, confirming Einstein's prediction from general relativity and opening up an entirely new way of observing the universe. But those detections have been from relatively small black holes. Stellar mass black holes formed from collapsing stars, merging in the modern universe. The mergers of supermassive black holes from galaxy collisions would produce much lower frequency gravitational waves, requiring different kinds of detectors, space-based interferometers that haven't been built yet but are planned for future decades. So when we look at MAX 647JD, we're seeing the beginning of a process that will take hundreds of millions of years to complete. We're catching it at the moment when the two proto-galaxies are just beginning their final approach, when they're close enough that merger is inevitable, but before the actual coalescence has occurred. It's like watching two raindrops on a window slowly move toward each other, knowing that once they touch, they'll immediately combine into a single, larger drop, but capturing them at that instant just before contact. And the fact that this is happening so early in cosmic history, just 300 to 500 million years after the Big Bang, tells us something important about how structure formation proceeded in the young universe. It tells us that galaxies didn't form in isolation and then remain separate for billions of years. They formed in clusters, in groups, close enough together that they were gravitationally interacting from very early on. The universe wasn't a collection of neatly separated galaxies. It was a dynamic, interacting network of proto-galaxies, colliding, merging, exchanging material, building up larger structures through constant interaction. This is consistent with our understanding of cosmic structure formation, which begins with tiny density fluctuations in the early universe. Quantum fluctuations inflated to cosmic scales during the inflationary epoch, creating slight variations in density across space. Denser regions had slightly stronger gravity, which pulled in more matter, which made them even denser, creating a feedback loop that amplified the initial fluctuations over time. By the time the first stars were forming, the universe already had structure, regions that were slightly denser and less dense, arranged in a cosmic web pattern that computer simulations have beautifully reproduced. Galaxies formed preferentially in the denser regions, which meant they formed in groups, in clusters, close enough to each other that gravitational interactions and mergers were inevitable from very early on. And that's what we're seeing in MAX 647JD. Evidence that the cosmic web was already operating, already bringing proto-galaxies together, already initiating the mergers that would build larger structures. The early universe was busy, active, dynamic, not the quiet, empty place you might imagine from the phrase cosmic dark ages, but a cosmos alive with activity, with gas collapsing, stars forming, galaxies colliding, structure assembling at all scales. There's something almost frantic about the early universe's productivity, something that contrasts with the slower, more sedate pace of galaxy evolution in the modern cosmos. Most large galaxies in today's universe are already well established, their major mergers behind them, their current evolution more about slow accretion and gradual changes than dramatic collisions. The Milky Way's merger with Andromeda will be spectacular by modern standards, a major event that will reshape the local universe. But in the early universe, such mergers were routine, happening constantly, building up galaxies from smaller components through repeated collisions. It's the difference between a construction site and a finished building. The early universe was a cosmic construction site, actively assembling, constantly changing, pieces coming together to form larger structures. The modern universe is more like a finished city, still changing, still evolving, but more slowly, more subtly, the major construction mostly complete. But looking at Max 0647JD takes us back to that construction site, lets us witness the assembly in progress, see the building blocks coming together in real time, or at least in real time as it was 13 billion years ago, the light just now reaching us across the expanding universe. And the galaxy that results from this merger, the combined system that will exist a few 100 million years after the moment we're observing, that galaxy is probably still around today. It's had 13 billion years to continue evolving, to perhaps merge with other galaxies, to form new generations of stars, to build up into something much larger and more complex than the two small proto-galaxies we're seeing in Webb's image. It might be a massive elliptical galaxy now, orbited by its own system of smaller satellites. It might be part of a galaxy cluster, one of the largest gravitationally bound structures in the universe. Its stars, the stars that formed in that early merger, that burst into existence when the gas clouds collided. Those stars might still be shining, mature red giants now, or perhaps they've already died, returned their material to the interstellar medium, seeded new generations of stars. But in a very real sense, the galaxy we're looking at in Webb's image doesn't exist anymore, at least not in that form. We're seeing it as it was, frozen in time by the finite speed of light, preserved at that moment 13 billion years ago when two proto-galaxies were just beginning to merge. The actual objects in their present state are unimaginably far away and impossibly changed, transformed by billions of years of evolution into something we wouldn't recognize from this ancient portrait. That's the strange thing about astronomy. We're always looking at the past, never the present. The moon you see is the moon as it was 1.3 seconds ago. The sun is from 8 minutes ago. The nearest stars are from years ago, the distant stars from thousands of years ago, the nearby galaxies from millions of years ago, and these early galaxies from billions of years ago. We're looking through time, not just across space, assembling a history of the universe from light that's been traveling toward us since before Earth existed. So Max 0647JD is both real and gone, both observable and transformed, both a specific moment captured in light and a continuing story we can't see, unfolding in a present we can never observe directly. It's evidence of the early universe's dynamism, proof that galaxy mergers were happening from the very beginning, a data point in our understanding of how structure formed and evolved. And maybe that's enough to think about for now, that the universe we see is always a universe of the past, that looking outward in space means looking backward in time, that every observation is archaeology, every image a historical document from an earlier era of cosmic history. Rest now, knowing that the universe's story continues, whether we observe it or not, unfolding in the present we can never quite reach, always a step ahead of our light speed observations, always evolving, always changing, always building new structures from old materials, never finished, never complete, eternally a work in progress. The earliest galaxy merger we've ever seen is frozen in ancient light, but the process it represents continues everywhere, even now, even as you close your eyes. There's a particular element that feels essential to us, more than any other. We can live without gold, without uranium, without most of the periodic table. But oxygen, we need it constantly, every few seconds, drawing it into our lungs, binding it to hemoglobin, transporting it to cells where it enables the metabolic processes that keep us alive. Without oxygen for just a few minutes, consciousness fades, brain cells begin dying, life itself becomes impossible. So there's something deeply resonant about the discovery that James Webb made in March 2025. The detection of oxygen in JDES GS Z14-0, the most distant galaxy ever observed, existing just 290 million years after the Big Bang. This wasn't just any oxygen detection, it was the most distant observation of this element ever made, pushing back the timeline of when heavy elements appeared in the universe by hundreds of millions of years. But let me explain why this matters, because it's not immediately obvious why finding oxygen in an ancient galaxy should be significant. After all, we find oxygen everywhere in the modern universe. It's the third most abundant element overall after hydrogen and helium. About 1% of all atoms in the universe are oxygen. It's in water, in rocks, in atmospheres, in organic molecules, in you. Finding oxygen seems almost mundane, like finding sand on a beach. Except that oxygen wasn't always there. None of the heavy elements were. When the universe began, in that first brilliant instant of the Big Bang, only the lightest elements formed, mostly hydrogen, some helium, traces of lithium and beryllium, and essentially nothing else. The early universe was too hot for atoms to form at all for the first 380,000 years, and when it finally cooled enough for atoms to exist, about 75% of the matter was hydrogen and 25% was helium. That was it. That was the entire chemical inventory of the early cosmos. No carbon, no nitrogen, no oxygen, no iron, no silicon. Nothing that makes rocky planets possible. Nothing that makes complex chemistry possible. Nothing that makes life, at least life as we understand it, possible. Just the simplest elements, the ones that could be forged in the intense heat and pressure of the Big Bang itself. Everything else had to be made later, in stars. Stars are element factories, alchemical furnaces that transform lighter elements into heavier ones through nuclear fusion. In a star's core, hydrogen fuses into helium, releasing energy in the process. That's what makes stars shine. What makes the sun warm our planet. What powers the light of every star you see in the night sky. But in massive stars, stars significantly larger than the sun, the process continues beyond hydrogen fusion. When a massive star exhausts its hydrogen fuel, its core contracts and heats up until it's hot enough to fuse helium into carbon. This requires higher temperatures than hydrogen fusion, about 100 million degrees Kelvin instead of the 10-15 million degrees needed for hydrogen fusion. And it produces less energy, so it proceeds faster, burning through the helium fuel in thousands or millions of years instead of billions. Then, if the star is massive enough, the process continues. Carbon fuses into oxygen, neon, magnesium. Oxygen fuses into silicon and sulfur. Silicon eventually fuses into iron. Each successive stage requires higher temperatures, proceeds faster, and produces less energy. The final stage, silicon fusion, might last only a few days before the star's core is converted entirely to iron. and iron is where fusion stops being energetically favorable. Fusing iron actually consumes energy instead of releasing it, so there's no energy source to support the star against gravitational collapse. The core collapses catastrophically, and the outer layers rebound in a supernova explosion, one of the most violent events in the universe, briefly outshining entire galaxies, releasing more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. And that explosion, that supernova, scatters all those newly forged heavy elements into space. The carbon, the oxygen, the nitrogen, the silicon, the iron, all the elements from the periodic table up to iron, plus elements heavier than iron that are only formed in the extreme conditions of the supernova itself. They're all blown outward at tremendous speeds, mixing with the interstellar medium, enriching the gas clouds that will form the next generation of stars. This is how the universe builds its chemical inventory. Each generation of massive stars lives fast, dies violently, and enriches the cosmos with heavy elements. The next generation of stars forms from gas that's slightly more enriched, forms planets around those stars that contain heavy elements, eventually produces rocky worlds where complex chemistry can occur, where life might arise, where consciousness might develop and look back at the cosmos and figure out its own origins. So oxygen in the universe is a marker of stellar processing. It's evidence that at least one generation of massive stars has lived and died, has gone through its complete life cycle, has fused hydrogen into helium, into carbon, into oxygen, has exploded in supernovae, has scattered its enriched material back into the interstellar medium. Finding oxygen means finding evidence of that whole cycle having already occurred. And Webb found oxygen in a galaxy from just 290 million years after the Big Bang, in the earliest cosmic dawn. In that period when the universe was supposedly just beginning to form its first structures. This means that the stellar cycle, star formation, fusion, supernova, enrichment, had already gone through at least one complete iteration by that incredibly early time. Let me emphasize how fast that is. Massive stars, the ones that produce oxygen and explode as supernovae, live for only millions of years, sometimes as little as a few million years for the most massive ones. So the oxygen Webb detected means that stars had formed, lived their entire lives, and exploded, all within less than 290 million years after the Big Bang. The universe wasted no time getting started with the great cosmic recycling program, but even that's not quite fast enough to explain what we see. You need time for the first stars to form, time for them to live and die, time for their ejecta to mix with surrounding gas, time for new stars to form from that enriched material, time for enough cycles to build up the amount of oxygen we're detecting. And doing all of that in less than 290 million years requires impressive efficiency, rapid star formation, quick cycling of material through stellar generations. It suggests that the early universe was remarkably productive, forming stars at high rates, cycling material efficiently, building up heavy element abundances faster than our models predicted. It's another piece of evidence, like the massive early galaxies we discussed earlier, that the infant universe was precocious, accomplishing in a few 100 million years what should have taken longer according to our theoretical models. And there's a personal connection here, one that makes this discovery feel more significant than just another spectral line detected in an ancient galaxy. The oxygen Webb found oxygen atoms formed in massive stars 13.5 billion years ago, scattered through space in supernova explosions, mixed with the interstellar medium, incorporated into subsequent generations of stars and planets. That oxygen is chemically identical to the oxygen you're breathing right now. Not the same atoms, obviously. The atoms in JDA's GS Z140 are still there, 13.5 billion years later, probably incorporated into stars in some modern galaxy impossibly far away. But they're the same kind of atoms, made by the same process, following the same physics, products of the same stellar alchemy that produce the oxygen in Earth's atmosphere, in water, in your body. Every breath you take contains oxygen atoms forged in stars that lived and died before the sun formed. Those atoms were ejected into space in supernovae, drifted through the galaxy for millions or billions of years, were incorporated into the molecular cloud that collapsed to form our solar system, were gathered into the proto-Earth, were released by photosynthetic organisms into the atmosphere, were cycled through ecosystems, and are now temporarily in your lungs before being exhaled and continuing their journey through Earth's biosphere. The atoms in you are ancient, not just old, ancient in the cosmic sense. They've existed since the first generations of stars began producing heavy elements, been recycled countless times through stars and planets and living things, accumulated histories we can never fully trace, collected stories written in nuclear reactions and chemical bonds. And when Webb detected oxygen in JDA's GS Z140, it was detecting evidence of that process beginning, of the first cycles of stellar alchemy that would eventually produce the chemical inventory necessary for planets, for life, for you. It's a connection across 13.5 billion years and unimaginable distances, a thread linking the earliest generations of stars to this present moment. To you reading or listening to these words, breathing oxygen that shares a history, if not specific atoms, then at least a common origin, with oxygen forged in the cosmic dawn. The universe has been running this program for almost its entire history. Make stars, fuse elements, explode, enrich, repeat. Each cycle adds more heavy elements to the cosmic mix, gradually increasing the metallicity, as astronomers call it. Any element heavier than helium is a metal in astronomical terminology, which confuses chemistry students, but makes sense in terms of stellar physics. The first stars were pure hydrogen and helium, completely metal-free. The second generation had traces of heavier elements. Each successive generation had more, building up the chemical complexity over billions of years. Our solar system formed from material that had been through many such cycles. The sun's metallicity is fairly high by cosmic standards, reflecting billions of years of stellar processing in our galaxy before the solar system formed. All those heavy elements, the iron in Earth's core, the silicon in its crust, the carbon in your cells, the calcium in your bones, all of it was made in stars, scattered by supernovae, gathered together 4.6 billion years ago when the solar nebula collapsed, incorporated into planets, and eventually on at least one planet, organized into living systems complex enough to understand their own atomic origins. It's remarkable, really, how the universe bootstrapped itself from simplicity to complexity, started with just hydrogen and helium, used gravity to make stars, used stars to make heavier elements, used those elements to make planets, used planets to provide environments where complexity could develop, used complexity to generate life, used life to produce consciousness, used consciousness to figure out the whole story. The universe apparently needed to exist for nearly 14 billion years before it could understand itself, and it accomplished that understanding by organizing some of its atoms into patterns capable of self-reflection. And oxygen was crucial to that process, at least on Earth. Photosynthesis produces oxygen as a waste product, and that oxygen accumulated in Earth's atmosphere starting about 2.4 billion years ago, transforming the planet's chemistry and enabling the evolution of complex energy-intensive organisms like animals. Without oxygen, without the great oxygenation event, without photosynthetic organisms releasing this waste product into the atmosphere, you wouldn't be here. Neither would any complex multicellular life as we know it. So oxygen is more than just another element in the periodic table. It's a necessary precursor to complexity, at least in the one example we know, Earth, and finding it in the most distant galaxy we've ever observed. In the earliest cosmic epoch we can see, means that the universe was already preparing the groundwork for complexity, already manufacturing the necessary ingredients, already setting up the chemical inventory that would eventually make life possible, all within just a few 100 million years of its beginning. Whether life arose elsewhere, whether oxygen is necessary for all forms of life, or just the particular form that evolved on Earth, whether consciousness is common or unique, these remain open questions. But what's certain is that the universe has been making oxygen since very early in its history, scattering it through space, incorporating it into new stars and planets, providing the raw materials for complex chemistry wherever conditions allow. And now you know that the oxygen you're breathing has a history that stretches back to the cosmic dawn, to the first massive stars in the first galaxies, to stellar furnaces that burned 13.5 billion years ago in a universe barely out of its infancy. You're connected to those ancient stars through chemistry, through physics, through the great cycle of stellar birth and death that's been running since the universe first learned how to make structure from simplicity. Breathe deeply now. Feel the oxygen entering your lungs, binding to hemoglobin, traveling to cells, enabling the metabolic processes that keep you alive. And know that those atoms are veterans of cosmic history, survivors of supernovae, witnesses to the evolution of galaxies, links in an unbroken chain connecting the earliest stars to this present moment. The universe makes oxygen continuously, tirelessly, through stellar fusion and violent explosions, ensuring that the chemical ingredients for complexity remain available, remain abundant, remain ready for whatever new structures might arise, whatever new forms complexity might take, whatever new instances of consciousness might develop, and wonder about their origins. Rest now, breathing atoms forged in ancient stars, connected through chemistry to the deepest history of the cosmos. Sometimes the universe arranges itself into patterns so perfect they seem intentional, so geometric they could be designs. The rings of Saturn, for instance, those beautiful flat bands of ice and rock circling the planet in neat layers, separated by gaps, organized into structures that look almost engineered, or the hexagonal storm at Saturn's North Pole, a six-sided jet stream persisting for decades, its geometric perfection seeming to defy the usual chaos of weather systems. And then there's Fomalhaut, a young star about 25 light-years away in the constellation Pisces Austrinus, which James Webb has revealed to be surrounded by not one, not two, but three nested rings of debris, a cosmic archery target, a bullseye in space, circles within circles extending outward from the central star in a pattern so clean and organized it immediately demands explanation. Fomalhaut isn't a particularly unusual star. It's about twice the mass of the Sun, about 16 times more luminous, and about 440 million years old, young compared to the Sun's 4.6 billion years, but old enough to have completed its initial formation phase and settled into stable main sequence hydrogen fusion. It's bright enough to be easily visible to the naked eye from Earth, one of the brightest stars in the autumn sky if you're viewing from the northern hemisphere, though it's relatively far south in the sky and better viewed from southern latitudes. But what makes Fomalhaut fascinating isn't the star itself, it's what surrounds it. Astronomers have known for decades that Fomalhaut is circled by a disk of debris, material left over from the star's formation or produced by collisions between larger objects. But previous observations, even with powerful telescopes like Hubble, could only see the outermost, brightest ring, a narrow band of material about 140 astronomical units from the star, 1 astronomical unit being the Earth-Sun distance. So this ring is 140 times farther from Fomalhaut than Earth is from the Sun. Webb, with its infrared vision and unprecedented sensitivity, revealed that there's much more structure than anyone had seen before. Inside that main ring are 2 additional rings, nested like Russian dolls, creating a 3-ring system that extends over distances 3 times the size of our entire solar system. The outermost ring is at about 140 AU, the middle ring at around 80 AU, and the innermost ring at perhaps 30-40 AU, all approximate, all fuzzy boundaries rather than sharp edges, but distinct enough to be clearly visible in Webb's images as separate structures. And rings like this don't just happen. They're not random. They're evidence of something shaping the disk, something organizing the debris into specific orbits, something clearing gaps and maintaining boundaries. And the something almost certainly is planets. Let me explain how this works because it's a beautiful example of orbital mechanics, of how gravity sculpts structure from chaos. When a star forms from a collapsing cloud of gas and dust, not all the material falls into the star. Material with too much angular momentum, material that's rotating too fast, can't fall directly inward. Instead, it settles into a disk around the star's equator, a flattened collection of gas and dust particles, all orbiting in roughly the same plane. And in that disk, dust grains collide and stick together. They form pebbles. Pebbles form boulders. Boulders form planetesimals, objects kilometers across, massive enough that their gravity begins to matter, massive enough to attract additional material. Planetesimals form protoplanets, sweeping up material in their orbital paths, clearing gaps in the disk as they grow. But the process isn't perfectly efficient. Lots of material remains, smaller objects that didn't get incorporated into planets, debris from collisions between planetesimals, ice and dust particles too far from the star for planets to form effectively. This leftover material forms debris disks, belts of small objects orbiting the star, similar to our solar system's asteroid belt between Mars and Jupiter, or the Kuiper belt beyond Neptune. And if there are planets in the system, their gravity shapes these debris disks. A planet's gravity affects objects in nearby orbits. either pulling them slightly inward or pushing them slightly outward, depending on the specifics of the orbital resonance. Over millions of years, this gravitational influence clears gaps in the disk, creates sharp edges, maintains ring structures. The planet acts like a shepherd, organizing the debris through repeated gravitational interactions, creating order from what would otherwise be a diffuse, unstructured disk. Saturn's rings work the same way. Many of the gaps in Saturn's rings correspond to orbital resonances with Saturn's moons, locations where a particle would orbit twice for every 3 times a moon orbits, or 3 times for every 5 times, or some other simple ratio. Those resonant orbits are unstable. Particles there get gradually nudged into different orbits, clearing gaps and sharpening ring edges. So Fomalhaut's 3 rings almost certainly mean there are planets in the system, probably at least 2 or 3 of them, each one maintaining one of the ring structures through gravitational shepherding. We can't see the planets directly. They're too faint, too close to the bright star to be easily detected, even with Webb's capabilities. But their effects are visible in the structure of the rings, in the gaps between rings, in the sharp inner and outer edges of each ring. This is indirect detection, inference from evidence rather than direct observation. But it's solid inference, based on well-understood physics and confirmed by countless examples in our own solar system and in other planetary systems we've studied. Where we see ring structures, we can confidently predict planets, even if we can't yet see them directly. And the system is surprisingly large, 3 times the diameter of our solar system, if you measure from the outermost ring. Our solar system's outer edge, if you count the scattered disk and Oort cloud, extends to maybe 50,000 AU or more. But the main planetary system, the region containing the 8 major planets, extends to about 30 AU, Neptune's orbit. Fomalhaut's organized debris extends to 140 AU, with structure visible all the way down to the innermost ring, suggesting a planetary system that's spread out over a much larger volume than our own. But then, Fomalhaut is a more massive star than the Sun, more luminous, with a stronger gravitational influence. It makes sense that its planetary system would be correspondingly larger, scaled up in proportion to the star's greater mass and brightness. The habitable zone around Fomalhaut, the region where temperatures would allow liquid water on a planet's surface, is farther out than ours, perhaps 6 to 7 AU instead of Earth's 1 AU, because the star is so much brighter. A planet in Fomalhaut's habitable zone would orbit much farther from its star than Earth does from the Sun, but would receive similar amounts of light and heat because the star is intrinsically more luminous. Whether there are planets in Fomalhaut's habitable zone, we don't know yet. The rings are all much farther out, in regions too cold for liquid water, more analogous to our outer solar system than our inner planets. But the existence of the rings suggests a substantial population of planets throughout the system, and there's no reason to think the inner regions are empty. It's likely there are rocky planets closer in, smaller and harder to detect but potentially present, orbiting in the warm inner regions where temperatures would allow complex chemistry and possibly even life. But life around Fomalhaut, if it exists, would have a limited time to develop. Stars more massive than the Sun have shorter lifespans. They burn through their hydrogen fuel faster because their greater mass creates higher core temperatures and faster fusion rates. Fomalhaut, at twice the sun's mass, will probably live for only about 1 billion years total before exhausting its hydrogen and evolving off the main sequence, expanding into a red giant and making life impossible on any planets. Earth took about 4 billion years to go from formation to complex multicellular life, and another 500 million years or so to produce technological civilization. If Fomalhaut's planets follow a similar timeline, they won't have enough time. The star will die before intelligence can arise, before consciousness can develop, before anyone can look up and wonder about those beautiful rings of debris visible in their night sky, reflecting starlight from their parent star. But maybe life doesn't always take 4 billion years. Maybe under the right conditions, with the right chemistry, in the right environment, it could develop faster. Maybe Fomalhaut's planets, if they exist and if they're habitable, will surprise us with rapid biological evolution, quick development of complexity, fast emergence of consciousness. Or maybe not. Maybe Earth's timeline is typical, and life around short-lived massive stars is simply impossible. The clock runs out before evolution has time to produce anything interesting. We don't know. That's one of the humbling aspects of studying planetary systems. We have exactly one example of a system with confirmed life, one data point, one instance to extrapolate from. We don't know if Earth's history is typical or unusual, if 4 billion years is a normal timeline, or surprisingly fast or frustratingly slow. We're trying to understand a phenomenon, the emergence and evolution of life, with a sample size of 1, which is scientifically frustrating but the best we can do until we find other examples. But what we do know is that planets are common. Nearly every star we look at carefully seems to have planets, and many of those planets are in configurations that could potentially allow liquid water, organic chemistry, maybe life. The universe is full of opportunities for life to arise, full of planetary systems forming and evolving, full of environments where complex chemistry might organize itself into self-replicating systems, where evolution might produce complexity, where consciousness might eventually emerge. Fomalhaut's rings are evidence of that ongoing planetary process, proof that our solar system isn't unique, confirmation that nature knows how to make planetary systems around all kinds of stars. The rings are a record of planet formation in progress, a snapshot of a stellar system still organizing itself, still clearing gaps and sharpening boundaries, still settling into its final configuration. And there's something aesthetically beautiful about those nested rings, isn't there? 3 concentric circles, perfectly aligned, centered on the star, creating a pattern that's both natural and geometric, both random and organized. It's art created by gravity, sculpture formed by orbital mechanics, beauty emerging from physical law. When you look at Webb's image of Fomalhaut, and you can find it easily online, it's publicly available like all Webb images. You're seeing structure that nobody designed, that formed spontaneously from the interactions of countless small objects over millions of years, shaped by invisible planets through invisible forces, organized by gravity into visible patterns. You're seeing order emerging from chaos, structure arising from randomness, beauty created by mathematics. The universe does this constantly, creates patterns, forms structures, organizes itself into configurations that strike us as beautiful. Spiral galaxies, planetary rings, crystal lattices, snowflakes, the double helix of DNA, the branching patterns of rivers and blood vessels and lightning bolts. Everywhere we look, we find patterns, structures that reflect the underlying mathematics of physical law, shapes that emerge when matter and energy interact under the constraints of physics. And Fomalhaut's rings are one more example, one more instance of the universe's tendency toward self-organization, toward creating structure from simplicity, toward building complexity from basic ingredients and simple rules. 3 rings around a young star, 25 light-years away, marking the presence of unseen planets, telling the story of a planetary system still forming, still evolving, still becoming whatever it will eventually be. Rest now, knowing that the universe is full of planetary systems, full of worlds forming around distant stars, full of opportunities for complexity to develop, for chemistry to explore new possibilities, for structure to emerge from chaos. Fomalhaut's rings are just one example among billions, one planetary system among the countless others filling our galaxy, each one unique, each one following the same physical laws, each one a variation on the theme of how gravity and rotation and chemistry work together to build worlds. The rings orbit on, patient and beautiful, marking time around a young star, waiting to see what their planetary system will become. There's something almost eerie about perfect alignment, especially when it occurs on cosmic scales where randomness seems more likely than order. When you flip a coin, you expect heads about half the time and tails the other half. That's randomness, statistical variation, the normal behavior of systems with no preferred orientation. But what if you flipped 100 coins and they all came up heads? You'd immediately suspect something was fixing the results, some hidden influence creating order where there should be chaos. And that's essentially what James Webb discovered in the Serpens Nebula, a stellar nursery about 1 in 400 light-years away in the constellation Serpens. The nebula is actively forming stars right now. Dozens of them, maybe hundreds, young protostars, still wrapped in their birth cocoons of gas and dust, still gathering mass, still in the early stages of stellar development. And many of these protostars are producing jets, narrow beams of material shooting outward at tremendous speeds, perpendicular to the protostar's circumstellar disks. These jets are a normal, expected feature of star formation. As material falls onto the forming star and into the disk around it, some of that material gets channeled along magnetic field lines and ejected outward at high velocities, carrying away excess angular momentum and allowing the star to continue growing without spinning itself apart. The jets emerge from the poles of the protostar, moving in opposite directions, creating a bipolar outflow that can extend for light years into the surrounding cloud. Every protostar makes jets, more or less. It's a fundamental part of the star formation process, as natural and expected as sparks from a campfire or steam from boiling water. What's not expected, what's deeply unusual, is for multiple protostars' jets to all point in the same direction, to be aligned with each other, to show a preferred orientation across the entire star-forming region. But that's exactly what Webb found in the Serpens Nebula. The jets aren't randomly oriented. They're not pointing in every direction like quills on a porcupine. They're aligned, all of them, or at least most of them, pointing in roughly the same direction, creating a pattern that NASA scientists described as being like sleet pouring down during a storm. All the streaks parallel, all the jets aligned, all showing the same preferred orientation. This is the first time we've directly observed this alignment phenomenon, though theorists had predicted it might occur. The alignment isn't perfect. There's some scatter, some variation in the exact orientations, but the overall trend is unmistakable. These jets are remembering something, recording something, preserving some property of their parent cloud that influenced their formation. And what they're remembering is rotation, the molecular cloud that these protostars formed from, the large-scale structure of gas and dust that fragmented into individual collapsing cores, was itself rotating. All clouds rotate, at least a little, because everything in the universe has some angular momentum, some net rotation inherited from the motions of larger structures or from turbulence in the interstellar medium. And when a rotating cloud fragments, when different regions collapse to form individual protostars, each collapsing core inherits some of that rotation. It's like a figure skater breaking apart into multiple smaller skaters. Each piece carries away some of the original angular momentum. Each piece spins in a direction related to the original rotation. The jets emerge perpendicular to the protostar's disk, and the disk is aligned perpendicular to the rotation axis of the collapsing core, which is related to the rotation axis of the parent cloud. So if multiple protostars form from the same cloud, and if they all inherit rotation axes aligned with the cloud's original rotation, then their jets should all be aligned too, all pointing in directions related to that original rotation axis. It's a record, preserved in the orientation of jets, of the cloud's rotation before it fragmented. The parent cloud has probably mostly dispersed by now, used up to form stars, or blown away by stellar winds and radiation. But the memory of its rotation persists in the aligned jets of its stellar children, like children remembering a parent's instructions, following directions given at birth, oriented by forces that no longer exist in their original form. And this tells us something important about star formation, something that's been suspected but never directly observed before. It tells us that star formation isn't a completely chaotic process, with each protostar forming independently without reference to its neighbors. There are coherent structures, large-scale patterns, properties of the parent cloud that influence the properties of the stars that form from it. Stars born together from the same molecular cloud are siblings in a very real sense. They share a common origin, a common chemistry, a common motion through the galaxy. They form at roughly the same time, in roughly the same place, from material that was mixed together before fragmentation, and they remember their shared origin in subtle ways, in their aligned spins, in their similar chemical compositions, in their correlated motions. Our own sun formed in a stellar nursery something like the Serpens Nebula, 4.6 billion years ago, probably along with hundreds or thousands of siblings. Those sibling stars have long since dispersed, scattered throughout the galaxy by their individual motions and by gravitational interactions with the galaxy's larger structures. They're no longer recognizable as a group. After 4.6 billion years, they've spread out across hundreds or thousands of light years, mixed in with other stars, lost their original cohesion as a cluster. But they still share some properties from their common origin. They have similar ages, all about 4.6 billion years old, formed within maybe 1 million years of each other, which is quite close by cosmic standards. They have similar chemical compositions, the same ratios of heavy elements, the same metallicity, because they formed from well-mixed gas in the same cloud. And somewhere in the galaxy, scattered among billions of other stars, there are perhaps a few hundred or a few thousand stars that are the Sun's true siblings, born from the same cloud, formed at the same time, sharing the same chemical heritage. We've tried to identify some of them, searched for stars with the right ages, the right compositions, the right orbital properties to have formed with the Sun. We've found a few candidates, stars that might plausibly be solar siblings, though confirming the relationship is difficult after 4.6 billion years of galactic motion and evolution. But they're out there, somewhere, the Sun's lost family, scattered through the Milky Way. And they were probably born with jets aligned with the Sun's jet, back when the Sun was a protostar, back when it was producing bipolar outflows and slowly gathering mass from its circumstellar disk. Those jets have long since dissipated, blown away into the interstellar medium, mixed with other material, recycled through later generations of stars. But for a brief period, geologically brief, cosmologically instantaneous, the baby Sun shot jets into space, aligned with the rotation axis of its parent cloud, parallel to the jets of its siblings, all of them recording the same rotational memory in their orientations. The Serpens Nebula is catching protostars at that stage right now, preserving that moment when jets are still flowing, when alignment is still visible, when the memory of the parent cloud's rotation is still written in the orientations of stellar outflows. It's a snapshot of a process that happened to the Sun 4.6 billion years ago, a glimpse of stellar birth at the stage when our solar system was forming, a view of the past preserved in present light. And there's something almost poetic about jets as memory, about orientation as history, about structure recording information in its geometry. The universe preserves information in unexpected ways, in the spin of galaxies, in the orbits of planets, in the alignments of jets, in the patterns of elements, in the structures of molecules. The past influences the present not just causally, but structurally, leaving fingerprints in the arrangements of matter, clues in the geometries of systems, hints in the correlations of properties. Astronomers are detectives, in a sense, reading those clues, interpreting those fingerprints, reconstructing the past from present observations. The aligned jets in Serpens tell us about the cloud's rotation before fragmentation, which tells us about the conditions in that part of the galaxy, which tells us about the processes that built the cloud from smaller components, which traces back through a chain of causation to earlier and earlier times, eventually connecting to the initial conditions set by the Big Bang itself. Everything connects. In cosmic history, every present configuration traces back to previous states, which trace back further, all the way to the beginning. The universe is a continuous story, a chain of causation linking the earliest moments to this present instant. Every structure containing information about its origin, every arrangement of matter recording something about the processes that created it. The jets in Serpens are young. The stars producing them are probably only a few 100,000 years old, maybe less. By stellar standards, they're newborns, barely begun, just starting their long lives as main sequence stars. In a few 100,000 more years, maybe a million, The jets will fade as the protostars finish gathering mass and settle into stable hydrogen fusion. The disks will gradually dissipate or form into planets. The nebula itself will be blown away by stellar winds and radiation, dispersing back into the interstellar medium. But the stars will remain, scattered over time from their birth cluster, drifting apart as they orbit the galaxy, gradually losing their original cohesion. In a few tens of millions of years, the cluster will have dissolved completely, the stars spreading out across that region of the galaxy, no longer recognizably associated with each other. But they'll still share properties from their common origin, similar ages, similar compositions, and somewhere in their histories, recorded in their early evolution, the memory of aligned jets from their birth in the Serpens Nebula. Memory takes many forms in the universe. Not cognitive memory, not the kind that involves neurons and experiences and recall, but structural memory, geometric memory, the preservation of information in the arrangements and motions of matter. The universe forgets nothing, in a sense. Every event leaves traces. Every process records information. Every structure embodies its own history. And we can read that history if we know how to look, if we have the right instruments, if we're patient enough to gather data and clever enough to interpret it. Webb's observation of aligned jets in Serpens is reading cosmic memory, decoding a message written in the orientations of outflows, interpreting information preserved in the geometry of star formation. It's a beautiful example of how observation and theory work together in science. Theory predicted that jets might be aligned if they formed from a rotating parent cloud. Observation confirmed it, showing that yes, the alignment exists, the memory is real, the structure preserves information just as theory suggested. And now we know something new about star formation, something that was suspected but not confirmed, something that moves our understanding forward incrementally, adding detail and nuance to our models. Science progresses through countless small steps like this. Predictions tested, observations made, theories refined, models improved. Each discovery adds a piece to the puzzle. Each observation answers one question while raising others. Each advance in instrumentation reveals new phenomena that require explanation. The process never ends because the universe is inexhaustibly complex, infinitely detailed, always capable of surprising us with new phenomena, unexpected patterns, structures we hadn't predicted. The Serpens Nebula is teaching us about star formation, about rotation, about memory preserved in structure. And in doing so, it's teaching us about our own origins, because the same processes that are forming stars in Serpens today formed the Sun 4.6 billion years ago. We're looking at our own past, seeing our own birth mirrored in distant protostars, understanding our origins by studying their formation. Rest now, knowing that the stars being born in Serpens will still be shining billions of years from now, long after human civilization has become a historical footnote, or a fossil record, or extinct species. Those stars will live for millions or billions of years, depending on their masses, fusing hydrogen into helium, generating light, warming planets, creating the conditions where life might arise, where complexity might develop, where consciousness might eventually emerge and look up at its own sky and wonder about its origins. The aligned jets flow on, recording rotation, preserving memory, telling their story to anyone patient enough to observe and interpret, anyone curious enough to wonder why they all point the same direction, anyone willing to see cosmic history written in stellar geometry. Sometimes the universe hands us a puzzle that doesn't fit any category we've created. We've spent decades, centuries even, building taxonomies of cosmic objects. Stars go here, galaxies go there, quasars fit in this box, black holes in that one. We've developed sophisticated classification systems, detailed models, comprehensive theories that explain most of what we observe. And then something new appears that doesn't quite fit anywhere, that seems to straddle categories, that possesses properties that shouldn't coexist according to our understanding. And astronomers, being scientists and therefore somewhat unimaginative when it comes to naming things, call these new objects exactly what they look like in the data: little red dots. James Webb has discovered over 300 of these mysterious objects scattered across the early universe, existing in that first billion years after the Big Bang, appearing in deep field images as exactly what their name suggests: small, red, point-like sources that don't behave like normal galaxies and don't quite behave like quasars either. There's something else, something new, something that's forcing astronomers to reconsider their models of how supermassive black holes and galaxies form and evolve in the early universe. Let me explain what makes these little red dots so puzzling, because it's not immediately obvious why astronomers are so confused by them. The confusion comes from their properties, specifically from the combination of properties that shouldn't logically coexist in the same object. They're compact, very compact. When we measure their sizes using Webb's high-resolution imaging, they appear to be only a few hundred light years across, tiny by galactic standards. The Milky Way is 100,000 light years in diameter. Even small dwarf galaxies are typically thousands of light years across. But these objects are much smaller, more like the size of a large star cluster than a proper galaxy. Yet they're incredibly luminous. They're pumping out enormous amounts of energy, far more than you'd expect from such small objects. A typical small galaxy might contain a few billion stars and emit a corresponding amount of light. But these little red dots are emitting as much light as much larger galaxies, despite their compact size, suggesting something extraordinarily energetic at their centers. And they're red. Not just slightly red, but very red in Webb's infrared observations, which could mean several things. It might mean they're highly dust-obscured, with the dust absorbing blue light and letting red light through, similar to how Earth's atmosphere makes sunsets red. Or it might mean they're dominated by old, cool stars that emit primarily red light. Or it might indicate specific spectral features, emission lines from hot gas that happen to fall in the red part of the spectrum. But here's where it gets weird. When astronomers examine the spectra of these objects, spreading their light out to see what wavelengths are present, they found evidence for both active, supermassive black holes and stellar emission. The objects show broad emission lines, characteristic of gas swirling around black holes at tremendous velocities, moving at thousands of kilometers per second, heated to millions of degrees by the intense radiation and gravitational forces near the black hole. But they also show emission from stars, from stellar populations that seem to be forming actively or that formed recently. This combination is unusual. Quasars, the extremely luminous cores of galaxies powered by supermassive black holes actively consuming material, typically outshine their host galaxies so completely that you can't see the stars at all. The black hole's glare drowns out everything else, like trying to see a candle next to a searchlight. But in these little red dots, both components are visible, the black hole emission and the stellar emission, at comparable brightnesses. And when astronomers tried to measure the black hole masses from the observed velocities and luminosities, they got numbers that seemed impossibly large for such early cosmic times and such small host systems. Some of these little red dots appear to contain black holes with tens or hundreds of millions of solar masses, existing less than 1 billion years after the Big Bang, in host systems barely larger than star clusters. That's a problem. Black holes aren't supposed to grow that massive that quickly in systems that small. Supermassive black holes, the kind with millions or billions of solar masses, are found in the centers of large galaxies, and we think they grow over billions of years through a combination of gas accretion and mergers with other black holes. Building 100 million solar mass black hole in less than 1 billion years requires either extremely efficient accretion rates or some alternative formation mechanism that doesn't involve starting from stellar mass black hole seeds. And then there's the most puzzling example, an object nicknamed QSO-1, discovered in July 2025, which appears to be essentially a naked supermassive black hole, a 50 million solar mass black hole with almost no surrounding galaxy, or at least no galaxy visible in Webb's observations. It's producing a quasar-like spectrum, clearly an active black hole consuming material, but the expected stellar population that should form the host galaxy is either absent or extremely faint. This is deeply weird. Black holes and galaxies are supposed to grow together, co-evolving through cosmic time, influencing each other's development. Every large galaxy we've examined in the nearby universe has a supermassive black hole at its center, and the black hole's mass is correlated with the galaxy's properties: its total stellar mass, the velocity dispersion of stars in its central bulge, various other measurements. The correlation is tight, suggesting that black holes and galaxies aren't just coincidentally found together, but are fundamentally connected in their growth and evolution. But QSO-1 seems to be a black hole without a galaxy, or at least without the galaxy we'd expect to see given the black hole's mass. It's as if someone built the engine without building the car, created the black hole without creating the surrounding stellar system that should have formed alongside it. Several theories are trying to explain these little red dots, and astronomers are actively debating which explanation is correct, or whether some combination of explanations is needed, with different little red dots representing different phenomena that happen to look similar in our observations. One possibility is that these are heavily dust-obscured galaxies, with normal stellar populations and black holes hidden behind thick clouds of dust that absorb most of the blue and ultraviolet light and re-emit it in the infrared. The compact appearance might be an illusion. Maybe we're only seeing the small, bright core, while the outer regions are too faint or too dust-obscured to detect. This would make them less mysterious, essentially normal galaxies seen under unusual conditions. Another possibility is that they're genuinely unusual objects, representing a different mode of galaxy and black hole formation that was more common in the early universe. Maybe in the first billion years after the Big Bang, conditions allowed for more efficient black hole growth, more rapid accretion, faster development of supermassive black holes than we see in later cosmic epochs. Maybe the early universe had different gas densities, different temperatures, different dynamics that enabled black holes to grow to large masses more quickly than current models predict. A particularly intriguing possibility involves something called direct collapse black holes. The standard story of supermassive black hole formation starts with stellar mass black holes, formed from the deaths of massive stars, which then grow over time by accreting gas and merging with other black holes. But this process is slow, taking hundreds of millions or billions of years to build up to supermassive scales. Direct collapse provides an alternative. Under specific conditions in the early universe, a massive cloud of gas might collapse directly into a black hole without first forming stars, creating a seed black hole with thousands or even millions of solar masses right from the start. These massive seeds could then grow to supermassive scales much more quickly than stellar mass seeds, potentially explaining how we see such massive black holes so early in cosmic history. QS01 might be an example of this, a direct collapse black hole that formed without an accompanying galaxy, or that formed before its host galaxy had a chance to build up significant stellar mass. If confirmed, it would be the first direct observation of a direct collapse black hole, providing crucial evidence for a formation mechanism that's been theoretically predicted but never definitively observed. Or maybe, and this is where it gets really speculative, maybe we're seeing the remnants of population 3 stars, the hypothetical first generation of stars that formed from pure primordial gas with no heavy elements. Population 3 stars were predicted to be extremely massive, hundreds of times the Sun's mass, burning brilliantly but briefly, before collapsing directly into black holes. If some of those black holes survived and grew, and if we're somehow seeing their signatures in these little red dots, it would provide the first observational evidence for population 3 stars, which have never been directly observed despite being a crucial prediction of stellar evolution theory. The truth is, we don't know yet. The little red dots are too new, too recently discovered, too puzzling to have definitive explanations. Astronomers are still gathering data, still analyzing spectra, still debating interpretations. More observations are needed, deeper images to see if there are faint outer regions we're missing, more detailed spectroscopy to understand the physical conditions, follow-up studies to track whether these objects evolve over cosmic time or remain stable. This is science in action, science at the frontier, where observations outpace theory and understanding lags behind discovery. It's uncomfortable in a way. We like having explanations. We prefer categories and models that fit our data neatly. But it's also exciting because puzzles like the little red dots are what drive scientific progress. They force us to reconsider our assumptions, refine our models, develop new theories that can accommodate observations that don't fit previous frameworks. And there's something almost delightful about the universe's ability to surprise us, to present phenomena we didn't predict, to reveal that our understanding, as sophisticated and detailed as it is, still has gaps, still has room for improvement, still can be enhanced by new observations and new thinking. The little red dots are humbling, in the best scientific sense. They remind us that the universe doesn't owe us easy explanations, doesn't conform to our expectations, doesn't arrange itself according to categories we've created based on limited observations of the nearby cosmos. They tell us that the early universe might have operated differently than we thought, that processes we understand in the modern universe might have worked differently in cosmic dawn, that our models, successful as they are at explaining most observations, might need significant revision to account for what Webb is revealing about the first billion years. And QS01, that naked black hole, is perhaps the most humbling of all. It sits there in the data, shining across 13 billion years, challenging our understanding of how black holes and galaxies form together. It's either an anomaly, one weird object that formed under exceptional circumstances, or it's the first example of a whole new class of objects, the tip of an iceberg of direct collapse black holes that could revise our entire understanding of supermassive black hole formation. Time will tell. More observations will accumulate. Theories will be refined or discarded. Eventually, we'll understand what little red dots are, how they form, what they tell us about the early universe. The process might take years or decades. Science moves slowly when dealing with distant, faint objects that require many hours of telescope time to study properly. But that's fine. The universe is patient. It's been waiting 13.8 billion years to be understood. It can wait a bit longer while we figure out what we're seeing. The little red dots will still be there in Webb's data, still puzzling, still mysterious, still waiting for the right explanation to emerge from the collaborative efforts of astronomers worldwide. And there's something comforting about that, actually, about knowing that the universe still has mysteries, still holds surprises, still contains phenomena we haven't fully explained. It means there's still work to do, still questions to answer, still discoveries waiting to be made. It means the scientific enterprise continues, that our understanding grows, that each generation adds to the accumulated knowledge of the species. The little red dots are dots of mystery in our cosmic understanding, gaps in our knowledge, puzzles waiting to be solved, and solving them, figuring out what they are, how they formed, what they tell us about the early universe, will add new chapters to our cosmic story, new details to our understanding of how the universe evolved from the Big Bang to the present. Rest now, knowing that the universe is more complex than we realized, more surprising than we expected, more capable of challenging our understanding than we might like. The little red dots shine in Webb's images, small and red and mysterious, patient witnesses to the early universe's processes, waiting for us to figure out their secrets. The universe asks questions through its observations. We answer slowly, carefully, building understanding piece by piece. And somewhere in that dialogue between observation and theory, between data and interpretation, between what we see and what we understand, science advances, knowledge grows, and the cosmos gradually yields its secrets to persistent inquiry. Planets come in a bewildering variety, far more diverse than anyone imagined before we started discovering them around other stars. For most of human history, we knew only one planetary system, our own, and we naturally assumed it was typical, representative, perhaps even the only possible configuration. We had rocky planets close to the sun, gas giants farther out, ice giants beyond them, a neat arrangement that seemed logical, orderly, natural. And then we started finding exoplanets, and the universe revealed just how wrong our assumptions were. We found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, completing their years in days rather than months or years. We found super-Earths, rocky planets more massive than Earth but smaller than Neptune, a category that doesn't exist in our solar system at all. We found planets orbiting binary stars, planets with wildly eccentric orbits, planets so close to their stars that their surfaces are molten, planets so far from their stars that they barely receive any starlight at all. The diversity is staggering, humbling, a reminder that nature explores the full possibility space of planetary configurations, not just the one example we happen to grow up with. And among this diversity, there are extremes, planets that push physical processes to their limits, that exist in conditions so harsh they challenge our understanding of how matter behaves. WASP 18b is one such extreme. It's a hot Jupiter orbiting a sun-like star about 400 light-years away, but calling it merely hot undersells just how extreme this world is. The planet orbits incredibly close to its star, only about 3% of the Earth-Sun distance, or about 2.7 million miles, roughly 3 times the star's radius. At that distance, it completes an orbit in less than 23 hours. Its year is shorter than our day. And the temperatures are beyond anything we experience in our solar system. The day side of WASP 18b reaches approximately 5,000 degrees Fahrenheit, about 2,750 Kelvin, hot enough to vaporize iron, hot enough to glow red hot if you could somehow see it directly. For comparison, lava on Earth is typically around 2,200 degrees. The surface of Venus, the hottest planet in our solar system, is about 900 degrees. WASP 18b is in a completely different regime of temperature, hot enough that chemistry as we know it breaks down, hot enough that even stable molecules fragment and decompose. And that's exactly what happens to water there, if water can even temporarily exist at those temperatures. James Webb observed WASP 18b in 2024 and created the first three-dimensional atmospheric map of an exoplanet, tracking how temperature, composition, and wind patterns vary across the planet's surface and with altitude. And what Webb found was a world of chemical destruction, a planet where molecules are continuously torn apart and reformed in an endless cycle of fragmentation and recombination. At 5,000 degrees, water molecules, H2O, that stable compound that covers most of Earth's surface and fills our cells, and seems like one of the fundamental, unchanging features of chemistry. Water molecules literally rip apart. The thermal energy is sufficient to break the chemical bonds holding hydrogen and oxygen together, fragmenting water into its constituent atoms or into other molecular fragments like hydroxyl radicals, OH. This is called thermal dissociation, and it's a process that only occurs at high temperatures where thermal energy exceeds chemical bond energy. On Earth, in normal conditions, water is incredibly stable. You can heat it to boiling, you can freeze it to ice, you can subject it to pressure, and the H2O molecules remain intact. Only under extreme conditions, in flames, in plasmas, in regions of intense radiation, does water decompose into its component elements. But on WASP 18b, those extreme conditions are the normal environment. Water molecules don't last. They form briefly, perhaps, when hot oxygen and hydrogen atoms collide with the right energy and orientation. But within nanoseconds or microseconds, thermal energy breaks them apart again. sending the fragments flying off to potentially form other molecules or to remain as free atoms until another collision occurs. Its chemistry in fast-forward, molecular formation and destruction happening on timescales far faster than the slow, stable chemistry we're familiar with. And it's not just water. Most molecules experience similar destruction. Carbon dioxide, methane, ammonia, anything with chemical bonds that can be broken by thermal energy. They all fragment and reform continuously, creating a churning atmosphere where molecular composition is constantly shifting, where nothing is stable, where chemistry is a dynamic process rather than a steady state. Webb's three-dimensional map revealed other fascinating features of WASP-18b's atmosphere. The planet is tidally locked, just like the Moon is to Earth. It keeps the same face toward its star at all times, completing one rotation per orbit. This creates a permanent day side and a permanent night side, with very different conditions on each hemisphere. The day side, as mentioned, reaches 5,000 degrees F, hot enough for thermal dissociation, hot enough that atoms move with tremendous velocities, hot enough that the atmosphere is continuously trying to escape into space. The night side is cooler, though cooler is relative. It's still over 3,000 degrees, hotter than most terrestrial furnaces. And between the two hemispheres, powerful winds blow at speeds exceeding 5,000 miles per hour, transporting heat from the day side to the night side, mixing atmospheric gases, creating circulation patterns that Webb could track by observing how the spectrum changed as the planet rotated. These winds are faster than Earth's jet streams by more than an order of magnitude. They're driven by the enormous temperature difference between the day side and night side. Hot gas expands and rises on the day side, flows toward the night side at high altitude, cools and sinks, then flows back toward the day side at lower altitudes, creating a circulation cell that wraps around the planet. The winds are so strong that they shift the hottest point on the planet slightly eastward of the substellar point, the location directly under the star, because hot gas is being blown downstream before it can re-radiate its energy. This three-dimensional map was a major achievement for exoplanet science. Previous observations could only give average properties: the planet's overall temperature, its average atmospheric composition, general characteristics. But Webb's sensitivity and spectral resolution allowed astronomers to map how these properties varied across the planet's surface and with altitude, creating a genuinely three-dimensional picture of an alien atmosphere. And what that picture revealed was a world utterly unlike anything in our solar system, a planet where conditions are so extreme that our intuitions about how planets should behave completely break down. WASP-18b doesn't have weather like Earth's weather. No storms in the sense of organized low-pressure systems, no clouds made of water or ice, no precipitation. Instead, it has high-altitude winds transporting molecular fragments, regions where different chemical species dominate depending on temperature and pressure. A dynamic atmosphere where molecular composition changes continuously. There might be exotic clouds, though, clouds made of materials that only condense at extremely high temperatures. Theoretical models suggest that hot Jupiters like WASP-18b might have clouds of vaporized metals or metal oxides, with iron or silicate grains condensing at high altitudes and then evaporating again as they fall into hotter layers. These clouds would be nothing like Earth's water clouds. They'd be thin, high-altitude hazes of exotic materials, barely visible, affecting the planet's spectrum in subtle ways that require precise measurements to detect. WASP 18b is obviously completely uninhabitable. Nothing remotely like life as we know it could survive there. No organic molecules could remain intact. No liquid water could exist. No stable chemistry could occur. It's a planet that exists purely as an example of extreme physics, a natural laboratory for studying matter under conditions we can barely reproduce in terrestrial laboratories. But studying such extreme planets teaches us about the full range of planetary diversity, about what's possible in the universe's planetary menagerie. WASP 18b represents one extreme end of the hot Jupiter population, planets that are about as close to their stars as they can be without being destroyed by tidal forces or stellar radiation. Closer, and the planet would probably lose its atmosphere entirely, or spiral into the star, or be torn apart by tidal forces exceeding the planet's structural strength. So WASP 18b is near the survival limit, existing at the edge of what's physically possible for a gas giant planet. And studying it, mapping its atmosphere, measuring its composition, understanding its dynamics, helps us understand the physics of planetary atmospheres in extreme environments, which in turn helps us understand atmospheres in general, including Earth's atmosphere, which operates under much milder conditions but follows the same physical laws. There's a philosophical point here, too, about the nature of knowledge and how science advances. We learn about the normal by studying the extreme. We understand the typical by examining the exceptions. We comprehend the general principles by investigating the edge cases where those principles are pushed to their limits and where subtle effects become obvious. Earth's atmosphere is complex, influenced by countless factors: solar radiation, rotation, topography, ocean currents, vegetation, human activities. Disentangling all those influences and understanding the fundamental physics is difficult when everything is interacting at once. But on WASP 18b, many complications disappear. No oceans, no continents, no biology, no seasons, just the fundamental physics of how a tidally locked hot Jupiter's atmosphere responds to intense stellar radiation, and how molecular destruction and reformation proceed at extreme temperatures. It's a simplified system, in a sense, despite being so extreme, and simplified systems are easier to model, easier to understand, easier to use as tests of our theoretical frameworks. If we can correctly predict WASP 18b's atmospheric structure and dynamics, if our models can reproduce Webb's observations, then we can be more confident that we understand the underlying physics well enough to apply those models to more complex systems like Earth. So WASP 18b contributes to science not despite being extreme, but because it's extreme. It's a laboratory, a test case, an example that pushes our understanding and challenges our models. And the fact that we can observe it in such detail, creating three-dimensional maps of its atmosphere, tracking winds across its surface, measuring how molecular composition varies with temperature, is a testament to how far observational astronomy has advanced, how sophisticated our instruments have become, how much we can learn about worlds trillions of miles away from simple measurements of the light that reaches our telescopes. And there's something almost poetic about the impermanence of molecules on WASP 18b. the constant cycle of formation and destruction, the endless churning of chemistry that never reaches equilibrium. It's a reminder that stability is contextual, that what seems permanent and unchanging in one environment might be transient and fragile in another. Water seems eternal on Earth, filling oceans that have existed for billions of years, cycling through the atmosphere and biosphere, a permanent feature of our world. But on WASP 18b, water is ephemeral, fleeting, destroyed as quickly as it forms, unable to exist as a stable molecule in that infernal heat. Context matters. Conditions matter. The universe contains regions where matter behaves in ways utterly unlike what we experience in our everyday lives, where temperatures and pressures and radiation levels push physical processes into exotic regimes, where chemistry operates under rules we're still learning to understand. Rest now, grateful perhaps that you inhabit a planet where water is stable, where molecules persist, where chemistry is slow and steady enough to allow complex structures like your body to exist and maintain themselves over decades. You live in a realm of moderate temperatures, reasonable pressures, stable chemistry, conditions that are, cosmically speaking, quite rare and quite precious, necessary prerequisites for complexity to develop and for life to arise. WASP 18b reminds us that most of the universe is harsh, extreme, inhospitable to the delicate chemistries that make life possible. But that makes the places where conditions are just right. Planets like Earth, orbiting at just the right distance from stars just the right size, all the more remarkable, all the more worthy of appreciation. The molecular fragments on WASP 18b continue their endless dance of destruction and reformation, cycling through states faster than we can follow, creating a dynamic atmosphere unlike anything in our experience. And Webb watches patiently, recording spectra, mapping temperatures, teaching us about this alien world where even water cannot survive intact. There's something almost impossible to truly grasp about looking at light. When you switch on a lamp, the light reaches your eyes in about 3 nanoseconds, 3 billionths of a second. So fast it might as well be instant. The sunlight warming your face left the sun's surface 8 minutes ago. That's comprehensible, at least. You could watch a video in that time, have a short conversation, make a cup of tea. But what James Webb showed us in its very first science images, released to the world in July 2022, stretches the imagination into regions where numbers stop meaning much at all. The telescope captured the deepest infrared images ever taken of the universe, revealing thousands upon thousands of galaxies in a patch of sky you could cover with a grain of sand held at arm's length. And some of those galaxies, those tiny smudges of light, barely distinguishable from the cosmic background, appear as they were over 13 billion years ago. Let me put that another way, because 13 billion deserves to be said slowly. When the light now reaching Webb's mirrors first began its journey, our planet didn't exist. Our sun didn't exist. The Milky Way galaxy was still assembling itself from smaller collections of stars. The universe itself was only about 700 million years old, less than 6% of its current age of 13.8 billion years. It was an infant cosmos, still figuring out how to make galaxies, still learning the rules. And here's what makes this so beautifully strange. That ancient light has been traveling through expanding space, crossing distances so vast they make interstellar space look cozy, passing through clouds of gas and centuries of cosmic evolution, threading through the darkness for longer than the Earth has had a surface to stand on, all to reach a golden mirror hanging in space near a small blue world. Built by beings made of recycled stardust, who learn to capture photons and decode their secrets. Each pinpoint of light in those images represents an entire galaxy, not a star, not a planet, a galaxy. Hundreds of billions of stars gathered together by gravity, each star perhaps with its own planets, its own story of formation and evolution and eventual death. Most of these galaxies had never been seen by human eyes before that moment. They existed in the data, perhaps, predicted by models and theories, but they hadn't been witnessed, and now they have. It's a bit like opening a photo album from before you were born, before your parents were born, before your species existed, and yet somehow the album contains images of the house you'd eventually live in, still under construction. Except the scale is so much larger that analogies start to fail. The universe Webb reveals isn't just old. It's old in a way that makes human history feel like it happened in the last few seconds. If you compress the entire history of the universe into a single day, with the Big Bang occurring at midnight, Webb is showing us photographs from around 12:30 a.m. And humans, we don't show up until 11:59:96 p.m. There's a particular kind of peace in that perspective, I think. Your worries, my worries, all the accumulated anxieties of being a conscious being trying to navigate the complexities of modern life. They're all real, of course. They matter. But they're also unimaginably recent, occurring in a universe that operated for billions upon billions of years without the slightest concern for whether you'd remember to reply to that email or whether you said the right thing in that conversation. The light Webb captures is patient. It didn't hurry to get here. It couldn't. It moved at light speed, the universal constant, the cosmic speed limit. And even at that speed, it took most of the age of the universe to arrive. And now it's here, translated by engineers and scientists into images we can contemplate from the comfort of wherever you are right now. Maybe lying in bed, maybe watching the screen glow softly in the dark. When you look at those images, and you can find them easily enough, they're public, freely available, given to all of humanity as a gift from the collective effort of thousands of people across dozens of nations. You're not just looking at distant galaxies. You're looking at time itself, made visible. You're seeing the universe's childhood. You're witnessing the earliest chapters of the story that eventually, improbably, impossibly, led to you existing, to consciousness arising, to eyes opening in the cosmos that can look back at the cosmos and understand what they're seeing. Each of those thousands of galaxies in that grain of sand-sized piece of sky has its own history, its own population of stars being born and dying, its own chemistry, its own contribution to the great cosmic recycling program that takes hydrogen and helium and transmutes them through stellar alchemy into all the heavier elements that make planets and life possible. And they're just sitting there in the image, quiet and distant and patient, waiting to be studied, understood, appreciated. Perhaps in some of those galaxies, there are worlds where beings look up at their own night sky and wonder if they're alone. Perhaps they built their own telescopes, captured their own deep field images, and found our galaxy among the thousands they surveyed. Though they're seeing us as we were billions of years ago, long before we existed, to wonder about them. Perhaps they're sleeping too, under alien stars, dreaming dreams in ways we couldn't begin to imagine. Or perhaps not. Perhaps we're alone in this vast experiment, the universe's only audience for its own grand performance. Either possibility is overwhelming in its own way. But what's certain is that the light is real, the galaxies are real, the history is real, and it's all somehow more beautiful for being patient enough to wait 13 billion years to tell us its story. So rest now, knowing that in the grand cosmic timeline, rest is infinitely appropriate. The universe has been doing its work for eons. It can wait a bit longer while you close your eyes. There's something peculiar about permanence, about the illusion of unchangeability that cosmic objects seem to possess. When you look up at the night sky, at the constellations your ancestors saw thousands of years ago, at the nebulae and star clusters that have been photographed for over a century, it's easy to imagine that these structures are eternal, unchanging, fixed in their positions and forms like sculptures carved from the fabric of space itself. But nothing in the universe is truly permanent. Everything is in flux, everything is evolving, everything is temporary on some time scale. Stars are born and die, galaxies collide and merge. Even the constellations we recognize are slowly shifting as stars move through the galaxy at their own velocities, gradually distorting the patterns we've memorized and named and passed down through generations. And nebulae, those beautiful clouds of gas and dust, those stellar nurseries and supernova remnants, those photogenic structures that fill astronomy books and planetarium shows. Nebulae are particularly impermanent. They're made of diffuse gas, held together by gravity and pressure, but constantly being eroded by stellar radiation, dispersed by stellar winds, dissipated back into the interstellar medium from which they formed. The Horsehead Nebula is one of the most iconic such structures, a dark silhouette shaped remarkably like a horse's head, rising against the glowing background of the IC 434 emission nebula in the constellation Orion. It's about 1/300 light-years away, part of the vast Orion molecular cloud complex, one of the nearest regions of active star formation to our solar system. The Horsehead has been photographed countless times, from small amateur telescopes to the largest professional instruments, always recognizable, always striking, always somehow looking exactly like its name suggests, despite being a completely natural formation. But James Webb's observations of the Horsehead in unprecedented detail revealed something that changes how we think about this cosmic landmark. It's dying. More precisely, it's being eroded, eaten away by ultraviolet radiation from nearby stars, slowly dissipating into the surrounding space. And according to Webb's measurements and the models astronomers have constructed from that data, the Horsehead has only about 5 million years remaining before it's completely gone. 5 million years sounds like a long time, and by human standards, it certainly is. Longer than our species has existed, longer than most species persist in the fossil record, longer than recorded history by 3 orders of magnitude. But in cosmic terms, 5 million years is brief, a fleeting moment, barely a eye blink. The Horsehead Nebula has probably existed in recognizable form for a few million years already, which means we're seeing it in what's essentially the last half of its existence, witnessing it during its twilight years before it fades completely from the cosmic landscape. Let me explain what's happening to the Horsehead. Because the process is a beautiful example of how stellar radiation shapes the interstellar medium, how light itself can be a force that sculpts structure on galactic scales. The Horsehead is a dark nebula composed primarily of molecular hydrogen, along with dust grains and traces of other molecules. It appears dark not because it's intrinsically darker than surrounding space, but because it's dense enough to block light from the brighter emission nebula behind it, creating a silhouette effect. Behind the Horsehead, illuminating the background, is IC 434, an emission nebula, a region of ionized hydrogen gas glowing red from H-alpha emission, the characteristic wavelengths emitted when hydrogen atoms recombine after being ionized by ultraviolet radiation from hot, young stars. The stars doing the ionizing are part of the Orion OB1 Association, a group of massive, luminous stars born from the same molecular cloud, now emitting intense ultraviolet radiation that floods the region. That ultraviolet radiation doesn't just illuminate the gas, it erodes it. UV photons carry enough energy to break chemical bonds, to ionize atoms, to heat gas to thousands of degrees Kelvin. When UV radiation hits the dense molecular gas of the Horsehead, it gradually eats away at the nebula's surface, ionizing the outermost layers, heating them, causing them to expand and disperse into space. This process is called photoevaporation, and it's the same process that shapes many nebulae, that creates the distinctive edges and structures we see in regions of active star formation. The dense molecular gas is being eroded from the outside in, layer by layer, with the UV radiation continuously working its way deeper into the nebula, gradually reducing its mass, slowly destroying the structure. Webb's infrared vision revealed this process in unprecedented detail. At infrared wavelengths, Webb can see through the dust that makes the Horsehead opaque, invisible light, can detect the warm gas at the nebula's surface being heated by UV radiation, can map the temperature, structure, and chemical composition of the photoevaporating material. And what Webb saw was a nebula actively being destroyed, with its surface layers glowing from the energy of UV photons, with complex chemistry occurring at the interface between dense molecular gas and hot ionized gas, with the distinctive Horsehead shape being slowly eroded away. The mane of the Horsehead, that wispy structure at the top, is particularly vulnerable, being less dense and more exposed to UV radiation. The calculations suggest it will disperse first, perhaps within 1 million years or so. The main head structure, being denser, will last longer, but even it will eventually be completely photoevaporated, probably within 5 million years at current erosion rates. And then the Horsehead will be gone. Not destroyed in some catastrophic event, not blown away by a supernova or consumed by a collapsing cloud, but simply dispersed, eroded away to nothing. Its gas returned to the interstellar medium, its dust grains scattered among the stars, its distinctive shape lost forever, existing only in the countless photographs taken during its existence, and in whatever memories or records survive from our technological civilization. There's something poignant about that, isn't there? That this structure we've photographed and admired and named and shown to countless people in books and planetariums and websites, that it's temporary, doomed, in the process of disappearing even as we observe it. It's a reminder that even the seemingly eternal monuments of the cosmos are transient, that nothing lasts forever, that the universe is in constant flux even when that flux is too slow for individual humans to perceive. The Horsehead has been there for millions of years, looking roughly as it does now, a constant presence in the constellation Orion, visible to any observer with a telescope large enough to detect its dark silhouette. Humans have only known about it for about 130 years. It was first photographed in 1888 by Williamina Fleming at Harvard College Observatory, appearing on a photographic plate as a dark notch against the bright nebulosity. But long before humans noticed it, long before our species existed, long before primates evolved, or mammals diversified, or even dinosaurs walked the earth, the Horsehead was there, slowly forming from a dense knot in a larger molecular cloud, gradually taking on its distinctive shape through the combination of internal structure and external erosion. And it will still be there for millions of years after our current civilization has passed, assuming no cosmic catastrophe intervenes. Our great-great-great-grandchildren, thousands of generations removed, living in circumstances we can't imagine, with technologies we can't predict, they'll still be able to point their telescopes at Orion and see the Horsehead, perhaps slightly eroded, perhaps with its outlines subtly changed, but still recognizable, still distinctive, still there. But eventually, in 5 million years, give or take, it will be gone. Future astronomers, if there are any, whether human or descendant, species or alien civilizations that arise in the interim, they'll look at Orion and the Horsehead won't be there. They'll have to rely on historical records, on archives of images, on simulations of what it used to look like. The actual physical structure will be dispersed, its atoms scattered, its dust grains distributed among the stars, its distinctive shape erased from reality and preserved only in memory. This is the fate of all nebulae, really. They're inherently temporary structures, existing for millions or tens of millions of years before being dispersed by radiation, or blown apart by supernova shock waves, or consumed by star formation, or simply dissipated by the gradual expansion and mixing of interstellar gas. A few nebulae are younger, formed recently from supernova remnants, or planetary nebulae, just beginning their brief cosmic lives. Others are older, in advanced stages of dispersal, barely recognizable, fading into the background. The Horsehead is somewhere in the middle of its lifespan, not newly formed but not yet dissipated, visible and distinctive but clearly being eroded, in that twilight period where the end is visible but not yet imminent. We're fortunate, in a sense, to be observing the universe at this particular moment when the Horsehead still exists in recognizable form, when Webb can capture it in unprecedented detail, when we can study its chemistry and structure and evolution before it disappears. In some ways, the impermanence makes it more beautiful, doesn't it? If the Horsehead were truly eternal, unchanging, permanent beyond all timescales, it might be less precious, less worthy of appreciation. But knowing that it's temporary, that it's in the process of fading away, that future observers won't have the opportunity to see what we're seeing now, that knowledge adds poignancy, adds value, makes each observation more meaningful, because we know it's documenting something that won't always be available to document. This is true of many things actually, not just nebulae. The aurora borealis is more beautiful because it's ephemeral, appearing and disappearing on time scales of minutes or hours, never the same twice. Sunsets are more appreciated because they happen once per day and last only minutes, creating fleeting displays of color that change constantly and vanish into darkness. The cherry blossoms in Japan are celebrated partly because they bloom for only a week or two each spring, creating temporary beauty that must be appreciated immediately or missed for another year. Permanence and beauty aren't necessarily correlated. Sometimes beauty is enhanced by transience, by the knowledge that what you're seeing is temporary, that it will change or fade or disappear, that the opportunity to appreciate it is limited and therefore precious. The Horsehead Nebula is beautiful partly because of its shape, its contrast against the background, the way it resembles something familiar, despite being an entirely natural cosmic structure. But it's also beautiful because it's dying, because we know it's temporary, because its clock is running down, and eventually, not in our lifetimes, not in many lifetimes, but eventually, it will be gone, erased from the universe by the same stellar radiation that makes it visible against the glowing background. Webb's observations captured the Horsehead in what might be the finest detail ever achieved, revealing structure invisible to previous telescopes, showing the chemical complexity at its surface, mapping the temperature gradients as UV radiation heats the gas, documenting the photoevaporation process in action. These observations are scientific data, yes, providing measurements that constrain models of how radiation interacts with molecular gas, teaching us about the chemistry of photodissociation regions, advancing our understanding of star formation and nebular evolution. But they're also historical records, documentation of a cosmic structure during a particular phase of its existence, images that will outlast the object they depict, preserving the Horsehead's appearance for whatever future observers might want to study it or simply appreciate its beauty. Long after the actual Horsehead has dispersed, Webb's images will remain, archived in digital databases, stored in countless locations, representing this nebula as it appeared in the early 21st century, as measured from Earth, 1 to 300 years after the light left the nebula itself. There's a strange temporal displacement in astronomy, isn't there? We're observing the Horsehead as it appeared 300 years ago, in the early 8th century by Earth's calendar, when the light now reaching our telescopes first left the nebula. The actual nebula, in its present state, is unknowable to us. We won't see it as it is now for another 300 years, and by then our now will be 2,600 years in the past. We're always looking at the past when we look outward in space, always seeing history rather than present reality, always observing bygone states of objects that have continued evolving during the light travel time. So when we say the Horsehead has 5 million years remaining, we mean from its own time frame, not from ours. From our observational time frame, it has 5 million years, plus 300 years. We'll continue seeing it for that additional light travel time, even after it's actually dispersed, watching history unfold in delayed playback, seeing erosion that happened more than a millennium ago. It's confusing if you think about it too carefully, this mixture of timescales and reference frames and light travel delays. But in practice, for objects as close as the Horsehead, the light travel time is negligible compared to evolution timescales. The nebula isn't changing fast enough for the 300-year delay to matter much. We're essentially seeing it as it is, within reasonable approximation, watching its slow erosion in something close to real time by cosmic standards. and it will continue eroding, patient and slow, undisturbed by our observations or our appreciation or our documentations of its existence. The UV photons from Orion's hot stars will continue striking its surface, ionizing atoms, heating gas, causing photoevaporation, gradually reducing the nebula's mass and eroding its distinctive shape. The process is inexorable, unstoppable, inevitable, physics working according to its laws, energy flowing from high-temperature sources to low-temperature sinks, structure gradually giving way to disorder, as the second law of thermodynamics demands. But the gas won't be destroyed, just dispersed. The atoms that currently form the horsehead will continue existing, scattered through the interstellar medium, perhaps eventually incorporated into new clouds, new stars, new planets. The cycle continues. Nebulae disperse, enriching the interstellar medium, which collapses into new nebulae, forms new stars, creates new structures, disperses again, repeating endlessly as long as galaxies continue forming stars, and stellar radiation continues shaping the medium. The horsehead is one structure in that endless cycle, temporary and beautiful, distinctive and doomed, existing for a few million years before yielding its material back to the cosmic recycling program that builds and destroys and rebuilds across billions of years. Rest now, perhaps with a new appreciation for the temporary nature of cosmic structures, for the fact that even seemingly eternal monuments are slowly changing, gradually fading, eventually disappearing back into the universe from which they formed. The horsehead will continue its slow erosion, whether we observe it or not, counting down its remaining millions of years, unaware and unconcerned about its eventual dissolution. And maybe there's something comforting in that, in the knowledge that the universe operates according to its own timescales, its own processes, its own cycles of creation and destruction, completely independent of human concerns or human existence. The cosmos was here long before us and will continue long after us, building structures and dissolving them, creating beauty and eroding it away, following physical laws with perfect consistency across billions of years and countless cycles. The Horsehead Nebula is dying, slowly and beautifully, eroded by starlight, returning its matter to space, contributing to the eternal cycle of cosmic renewal. And we're here to witness it, to document it, to appreciate its transient beauty before it fades completely from view. Sometimes the universe gives us clean, simple answers that fit neatly into our theoretical frameworks, confirming what we predicted and reinforcing our confidence in our understanding. And sometimes, more often than we might like, the universe gives us puzzling answers that don't quite fit, that conflict with each other, that suggest either our measurements are wrong or our theories are incomplete. The Hubble tension is one of the most significant such puzzles currently facing cosmology, and in December 2024, James Webb's largest study of cosmic expansion rates confirmed that the tension is real, that it's not just measurement error or systematic bias or some quirk of specific methods. The universe is expanding faster than our best cosmological models predict, and the discrepancy is large enough and well measured enough that it's demanding serious attention from theorists trying to figure out what we're missing. Let me explain what the Hubble tension is, because it involves some of the most fundamental questions in cosmology. How fast is the universe expanding? How has that expansion rate changed over time? And what does that tell us about the universe's contents and ultimate fate? The expansion of the universe was discovered by Edwin Hubble in the 1920s, when he measured the distances and velocities of nearby galaxies, and found that more distant galaxies were receding faster than nearby ones, with velocity proportional to distance. This relationship, more distant means faster recession, is exactly what you'd expect if the universe itself is expanding, if space is stretching, carrying galaxies along with it like raisins in rising bread dough. The proportionality constant in that relationship, how much faster recession velocity increases per unit distance, is called the Hubble constant, usually written as h0 and measured in units of kilometers per second per megaparsec. It tells us the current expansion rate of the universe, how fast space is stretching at this present moment in cosmic history. Measuring h0 accurately has been a major goal of observational cosmology for decades. If you know the expansion rate, and if you know how that rate has changed over time, which depends on what the universe contains, matter, radiation, dark energy, etc., you can calculate backward to determine when the expansion began, how old the universe is, what its geometry is, what it will do in the future. But measuring h0 is tricky because it requires measuring both distances and velocities for many galaxies, and distance measurements in astronomy are notoriously difficult. There's no direct way to measure how far away a distant galaxy is. You can't stretch a measuring tape across intergalactic space. Instead, you have to use indirect methods, building a cosmic distance ladder where each rung relies on the previous one. The process starts with nearby measurements, parallax for the nearest stars, where we measure how their apparent positions shift as Earth orbits the Sun. Then we calibrate various standard candles, objects whose intrinsic brightness we think we know, so we can determine their distance by measuring how bright they appear, since apparent brightness decreases with distance squared. Cepheid variable stars are particularly useful. Their pulsation periods are correlated with their intrinsic luminosities. So measuring the period tells you the luminosity, and comparing that to the apparent brightness gives you the distance. Using cepheids, we can measure distances to nearby galaxies. Then we use those galaxies to calibrate even brighter standard candles, type Ia supernovae, which are exploding white dwarf stars that, under certain conditions, all reach roughly the same peak brightness. Type Ia supernovae are bright enough to be seen across billions of light years, so they can measure distances to very remote galaxies, allowing us to trace the Hubble relationship out to great distances and determine h0. This distance ladder method has been refined over decades, with Hubble Space Telescope making crucial contributions by observing cepheids in distant galaxies with unprecedented accuracy. The current best measurement using this method, led by Adam Rees and colleagues, gives h0 73 kilometers per second per megaparsec, with an uncertainty of only about 1 km/mpc. That's remarkably precise, better than 2% accuracy. But there's another way to measure h0, completely independent of the distance ladder, using observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, light from when the universe was only 380,000 years old. The CMB has a distinctive pattern of hot and cold spots that reflect sound waves in the primordial plasma, and by analyzing that pattern in detail, we can determine cosmological parameters, including the expansion rate, the universe's composition, its geometry, and we can predict what H0 should be today, given our best model of how the universe evolved from then to now. The Planck satellite made exquisite measurements of the CMB, and from those measurements, using the standard cosmological model, called LCDM, which includes dark matter and dark energy, we calculate that H0 should be about 67 kilometers SES MPC, about 9% lower than the distance ladder measurement. That might not sound like much, but given the precision of both measurements, it's a significant discrepancy, about 5 sigma in statistical terms, meaning there's only about a 1 in a million chance it's due to random error. This discrepancy is the Hubble tension. Two different methods, both seemingly reliable, both carefully calibrated, giving answers that differ by more than their combined uncertainties can explain. Either one method has some unidentified systematic error that's biasing the results, or the universe is more complex than our standard model assumes, with new physics or new components that affect the expansion rate in ways we haven't accounted for. Astronomers have been scrutinizing both methods intensely, looking for possible errors or biases. Maybe the distance ladder has problems. Maybe Cepheids don't all follow the same period luminosity relation. Maybe type Ia supernovae aren't quite as standard as we thought. Maybe there's contamination or selection bias or some subtle systematic effect we're missing. Or maybe the CMB analysis has issues. Maybe the standard cosmological model needs modification. Maybe there's new physics in the early universe that changes the predictions. Maybe our understanding of how the universe evolved from 380,000 years old to 13.8 billion years old is incomplete. But the more people have looked, the more both methods have held up. The distance ladder has been checked and rechecked, calibrated with different standard candles, tested for various biases, and it consistently gives H073. The CMB analysis has been scrutinized exhaustively, tested with alternative cosmological models, checked for foreground contamination or analysis artifacts, and it consistently predicts H067. And now Webb has added crucial new data. In December 2024, astronomers released Webb's largest study of cosmic expansion, using observations of Cepheid variables and type Ia supernovae in distant galaxies, to measure H0 with even better precision than Hubble Space Telescope could achieve. Webb's infrared vision and greater sensitivity allowed it to observe Cepheids in more distant galaxies, reducing uncertainties and testing whether the measurements might have been affected by crowding or confusion in Hubble's images. And Webb confirmed the higher value, H073 km s MPC, consistent with the distance ladder measurements, inconsistent with the CMB predictions. The Hubble tension is real. It's not a measurement error. It's not systematic bias in one method. Both methods are measuring correctly, but they're giving different answers, which means either our understanding of how the universe evolved is wrong, or there's new physics we haven't accounted for. So what could explain the discrepancy? Several possibilities are being explored, each with profound implications for fundamental physics. One possibility is early dark energy, a hypothetical component of the universe that had significant energy density in the early universe, but has since become negligible. If early dark energy existed, it would have affected the expansion rate in the early universe in ways that would change the predicted value of H0 derived from the CMB, potentially bringing it into agreement with the distance ladder measurements. But this would require adding new physics to the standard model, introducing a new component with specific properties tuned to solve the Hubble tension without disrupting all the other successful predictions of LCDM cosmology. Another possibility involves modifications to dark matter or dark energy. Maybe dark matter interacts with itself more strongly than we thought, or maybe dark energy evolves over time in ways not captured by the cosmological constant L. These modifications could change how the universe expanded over its history, potentially reconciling the different measurements of H0. Or maybe there are unknown particles or fields that affected the early universe, contributing to the energy density or modifying the expansion rate in ways that show up as a discrepancy between early universe measurements, like the CMB, and late universe measurements, like the distance ladder. The truth is, we don't know yet. The Hubble tension is an active area of research, with dozens of papers published annually proposing various solutions, testing different models, trying to find the missing piece that will reconcile the observations. It's one of the most important open questions in cosmology, potentially pointing toward new physics, new components of the universe, new understanding of how cosmic expansion works. And there's something exciting about that, isn't there? About knowing that our best models, as successful as they are at explaining most observations, are clearly missing something, that the universe has handed us a puzzle that demands new thinking, new theories, new approaches. This is how science advances, not by confirming everything we already believe, but by finding discrepancies, puzzles, tensions that force us to revise and improve our understanding. The Hubble tension might seem like a technical issue, a dispute over a few percent difference in a cosmological parameter. But it has profound implications. The expansion rate of the universe determines its age, its ultimate fate, the distances to all cosmic objects, the timeline of cosmic history. If H0 is really 73 rather than 67, that means the universe is expanding about 9% faster than we thought, which means it's younger than we calculated, about 12.7 billion years instead of 13.8 billion years, which creates other problems because some stars appear older than that age. Or maybe the expansion rate has changed over time in ways not captured by our current models, which would suggest new physics, new forces, new components of cosmic energy that we haven't yet identified. Either way, resolving the Hubble tension will likely require revising our understanding of fundamental cosmology, adding new pieces to our model of how the universe works. And Webb's contribution, confirming with its superior capabilities that the distance ladder measurements are solid, that the tension is real, is pushing the field toward recognizing that new physics is probably necessary. The problem isn't going to go away with more careful measurements or better calibrations. The measurements are fine. The observations are accurate. What needs to change is our theoretical understanding, our models of what the universe contains and how it evolves. This is both humbling and thrilling. Humbling because it reminds us that even our most sophisticated theories have gaps, that our understanding of the universe is still incomplete, that we're still learning fundamental things about cosmology despite decades of intensive research. Thrilling because it means there are discoveries waiting to be made, new physics waiting to be uncovered. revisions to our cosmic story that will emerge as we figure out what's causing the Hubble tension. Maybe there's a new component to the universe we haven't identified yet, some form of energy or matter that affects cosmic expansion but hasn't been detected directly. Maybe gravity works slightly differently on cosmic scales than general relativity predicts, requiring modifications to Einstein's theory. Maybe the early universe had properties we haven't accounted for, structures or fields or dynamics that influenced how it evolved from the CMB epoch to the present. Whatever the answer turns out to be, it will be significant. It will change how we understand cosmology. It will revise our cosmic timeline, our model of universal contents, our predictions for the universe's ultimate fate. And historians of science will likely look back at the Hubble tension as a turning point, the puzzle that forced cosmology to move beyond the standard LCDM model toward a richer, more complete understanding of cosmic evolution. For now, we have the measurements, the confirmed tension, the knowledge that something is missing from our models. What we don't have yet is the answer, the explanation that will reconcile the observations, reveal what new physics is operating, tell us what components or forces or phenomena we've been overlooking. But that answer will come eventually, through the patient work of observers and theorists, through new measurements and new models, through the gradual accumulation of evidence that will point toward the correct explanation. Science is slow but persistent, always making progress, always moving toward better understanding, even when that understanding requires admitting our current theories are incomplete. Rest now, knowing that the universe keeps secrets from us, that our understanding, vast and detailed as it is, still has important gaps, that mysteries remain to be solved and discoveries wait to be made. The Hubble tension is one such mystery, confirmed by Webb's observations, demanding explanation, pointing toward new physics that will deepen and enrich our comprehension of cosmic evolution. The universe expands faster than our models predict, and somewhere in that discrepancy lies a clue to something fundamental we haven't yet understood, something that will revise cosmology and advance our knowledge when we finally figure it out. For most of human history, planets were wandering lights in the sky, visibly different from stars, because they moved against the background of constellations, but otherwise mysterious, unknowable, except through their positions and brightness. Then telescopes revealed that planets were worlds, Jupiter with its moons, Saturn with its rings, Mars with its polar caps and seasonal changes. They became places, specific locations with features and characteristics, no longer just moving points of light, but actual physical objects in space. But they were still fundamentally remote. Even with the best telescopes, planets in our solar system are difficult to study in detail. We can see their surfaces or cloud tops, measure their sizes and masses, track their orbits, but understanding their atmospheres, their chemical compositions, their detailed properties required sending spacecraft there, getting close enough for direct measurements and analysis. And planets around other stars? For most of history, we didn't even know they existed. We assumed they probably did. Why would our solar system be unique? But we had no way to detect them, no way to confirm their existence, no way to study them. They were theoretical, plausible, but unobserved, existing in our imagination, but not in our data. That changed in the 1990s when the first exoplanets were discovered orbiting other sun-like stars, detected through the subtle gravitational wobbles they induced in their parent stars, or through the tiny dips in starlight when they transited in front of their stars as seen from Earth. Suddenly, exoplanets were real, confirmed, measurable, and the discoveries came rapidly. Hundreds of exoplanets, then thousands more, revealing that planets are common, that nearly every star has planets, that planetary systems fill the galaxy and presumably the universe. But even after we knew exoplanets existed, even after we'd measured their masses and sizes and orbital periods, they remained mysterious in many ways. We could infer basic properties, whether they were rocky or gaseous, hot or cold, large or small. But we couldn't study their atmospheres directly, couldn't measure their chemical compositions, couldn't determine what molecules were present in their skies. Until James Webb, until an infrared telescope sensitive enough and precise enough to detect the faint light from exoplanet atmospheres, to spread that light into spectra, to identify the specific wavelengths absorbed or emitted by molecules in those distant skies. And in November 2022, just a few months after beginning science operations, Webb detected carbon dioxide in the atmosphere of WASP 39b, a hot Jupiter 700 light-years away, orbiting its star every 4 days. This was the first unambiguous detection of CO2 on any exoplanet, the first time a specific molecule had been definitively identified in an alien atmosphere using spectroscopy. That might not sound revolutionary. Carbon dioxide is common, familiar, present in Earth's atmosphere and Venus's atmosphere and Mars's atmosphere. But the significance wasn't the molecule itself. It was what the detection represented. Proof that Webb could identify specific molecules in exoplanet atmospheres, that we now had the capability to do atmospheric chemistry on worlds we'll never visit, that we could study alien skies in detail despite the planets being trillions of miles away and separated from their stars by only tiny angular distances as seen from Earth. Let me explain how this works because it's remarkably clever, exploiting the physics of light and absorption and transmission through gases. When an exoplanet transits in front of its star, passes between the star and Earth, most of the star's light is blocked, creating a tiny dip in the star's brightness. But some of the star's light passes through the planet's atmosphere before reaching us. And that light carries information about what molecules are present in the atmosphere. Different molecules absorb light at different wavelengths. CO2 absorbs strongly at specific infrared wavelengths, corresponding to the energies needed to make its molecules vibrate or rotate in specific ways. Water vapor absorbs at different wavelengths, methane at others, ozone at others. Each molecule has its own characteristic absorption pattern, its own spectral fingerprint that identifies it uniquely. So by spreading the light into a spectrum and looking for which wavelengths are absorbed more strongly when the planet is transiting than when it's not, we can identify which molecules are present in the planet's atmosphere. The deeper the absorption at a particular wavelength, the more of that molecule is present. By analyzing the full spectrum, we can determine atmospheric composition, estimate abundances, even constrain temperature and pressure profiles. Webb detected CO2 in WASP 39b by observing multiple transits, gathering enough data to measure the tiny additional dimming at CO2's absorption wavelengths compared to wavelengths where CO2 doesn't absorb. The signal is incredibly small. We're talking about changes in brightness of perhaps a few tens of parts per million, detectable only because Webb is so sensitive and because the observations were planned carefully to maximize signal-to-noise. But it worked. The CO2 absorption was clearly visible in the spectrum, unambiguous, matching the wavelengths predicted by molecular physics. Carbon dioxide was confirmed in an alien atmosphere, detected across 700 light-years, identified with the same certainty that laboratory spectroscopy identifies molecules in samples here on Earth. And then Webb kept going. The same observations that detected CO2 also detected water vapor, sodium, potassium, and, most remarkably, sulfur dioxide, SO2, a molecule created by photochemistry in the planet's upper atmosphere. This was a major discovery because sulfur dioxide on WASP 39b isn't a residual component from the planet's formation. It's actively being created by chemical reactions driven by starlight. Similar to how Earth's ozone layer is created by UV radiation, breaking apart oxygen molecules. The detection of SO2 meant that Webb wasn't just detecting molecules that happened to be present in the atmosphere. It was detecting molecules created by ongoing chemical processes, witnessing atmospheric chemistry in action on an alien world. It meant we could study not just composition, but chemistry, not just what's present, but how molecules are created and destroyed, how photons drive reactions, how atmospheric processes operate under conditions completely different from Earth's. And WASP 39b was just the first. Webb has since observed dozens of exoplanet atmospheres, detecting molecules, in worlds ranging from scorching hot Jupiters to temperate sub-Neptunes, from giant gaseous planets to smaller rocky worlds. Each observation adds to our understanding of exoplanet diversity, of how atmospheres form and evolve, of what conditions allow different molecules to exist. Some planets show strong water vapor absorption, suggesting humid atmospheres rich in H2O. Others show methane, or CO, or complex hydrocarbons. Some show evidence for clouds, not water clouds like Earth's, but exotic clouds of vaporized metals or silicates, condensing at temperatures that would melt rocks on Earth. Some show signs of high-altitude hazes, layers of photochemical products created by stellar UV radiation, affecting how light passes through the atmosphere and how the planet appears in observations. Each planet is unique, with its own combination of composition, temperature, pressure, chemistry, cloud structure, and each one teaches us something about planetary physics, about how atmospheres work, about the processes that determine what molecules can exist under different conditions. But what astronomers really want, what drives much of exoplanet research, is to find biosignatures, chemical markers that might indicate life. On Earth, the presence of abundant oxygen in the atmosphere is a biosignature, created and maintained by photosynthetic organisms. Without life continuously producing oxygen, Earth's atmosphere would have almost no free O2. It would all react with rocks and organic materials, and be removed on geological timescales. The fact that our atmosphere is 21% oxygen is strong evidence for biology, for photosynthesis, for life producing a chemical disequilibrium that would be difficult to explain through non-biological processes. So astronomers are hoping to find oxygen, or ozone, O3, which forms from oxygen, or other potential biosignatures like methane and oxygen together. Since these two gases react with each other, and shouldn't coexist in large quantities without something, like life, continuously producing them. Or maybe more exotic biosignatures, molecules that life might produce under conditions different from Earth, chemical signatures we haven't thought of, but that might indicate biological activity in alien environments. Webb has the sensitivity to detect biosignatures if they exist in nearby potentially habitable planets. But the challenge is finding suitable targets, planets that are the right size, at the right distance from their stars, with atmospheres that transit and can be observed spectroscopically. Most known exoplanets aren't good candidates. They're too large, too hot, too far from their stars, or they don't transit from our viewing angle. But astronomers are searching, finding new candidates, prioritizing observations of the most promising targets. And eventually, maybe in the next few years, maybe longer, Webb or its successors will observe a rocky planet in the habitable zone of its star, spread its light into a spectrum, and detect oxygen or methane or some combination of molecules that's difficult to explain without invoking life. That will be one of the most significant discoveries in human history, finding evidence, indirect but compelling, that life exists beyond Earth, that biology isn't unique to our world, that the universe contains other instances of self-replicating chemistry, organizing itself into complex systems. It won't be direct detection. We won't see alien organisms or receive their radio transmissions or visit their worlds. But we'll have chemical evidence, spectral signatures suggesting that somewhere in that distant planetary system, processes are occurring that look an awful lot like biology, that match what we'd expect from life, creating chemical disequilibria in an atmosphere. And even if we don't find biosignatures, even if every potentially habitable planet we observe shows only abiotic chemistry, only lifeless atmospheres with compositions explained purely by geological and atmospheric processes, even that would be scientifically valuable, telling us something important about how common or rare life is, about whether Earth is typical or exceptional, about our place in the cosmic distribution of complexity. But for now, we have the capability, demonstrated and proven through Webb's observations of exoplanet atmospheres. We can identify specific molecules across hundreds or thousands of light years. We can study alien skies in detail, measure compositions, track chemistry, understand atmospheric processes on worlds we'll never visit directly. We've gone from barely knowing exoplanets exist to being able to analyze their atmospheres molecularly in less than 30 years. A remarkable acceleration of capability, a transformation in what's possible through careful engineering and clever observation strategies. WASP 39b will never be habitable. It's far too hot, a gas giant with no solid surface, orbiting so close to its star that its atmosphere is thousands of degrees. But it proved that atmospheric spectroscopy works, that we can detect molecules reliably, that the techniques are sound, and the instruments are capable. It was a test case, a demonstration, proof of concept for the larger program of studying exoplanet atmospheres and searching for signs of life. And somewhere out there, orbiting stars we haven't yet examined closely, there might be planets where the spectrum shows something unexpected, something suggestive, something that looks like life's chemical fingerprint impressed on an alien atmosphere. Webb is searching, observing, gathering data, building up our catalog of atmospheric compositions, learning what's normal and what's unusual. preparing us to recognize biosignatures when we finally see them. Or maybe we'll find that Earth-like biosignatures are rare or absent, that the galaxy is full of planets but empty of life, that whatever chain of unlikely events led to biology on Earth hasn't been replicated elsewhere, at least not in forms we can detect. That would be significant too, in its own way, though perhaps disappointing, forcing us to confront our possible uniqueness, our solitude in a vast universe of lifeless worlds. But either way, we'll know. That's what Webb's atmospheric observations give us. Knowledge, data, answers to questions that were purely speculative just years ago. Are there planets with atmospheres similar to Earth's? Yes, we're finding them. Can we detect specific molecules in those atmospheres? Yes, we've done it repeatedly. Are there signs of life? That remains unanswered, but we now have the tools to find out, the capability to search seriously rather than just speculating. Rest now, knowing that we're living through a remarkable era of discovery, a time when alien worlds are becoming knowable, when distant atmospheres are yielding their secrets, when the question of life beyond Earth is transitioning from philosophy to science, from speculation to observation. Webb continues its observations, pointing at distant planetary systems, gathering photons that pass through alien atmospheres, spreading those photons into spectra that reveal molecular compositions, building our understanding of the diversity of worlds filling the galaxy. Somewhere among those worlds, perhaps, life exists, and its presence is subtly altering atmospheric chemistry in ways that will eventually show up in our spectra, in our data, in our growing catalog of alien atmospheres. And when that happens, when we find the first compelling evidence for biology beyond Earth, it will mark one of the great transitions in human understanding. The moment when we learned we're not alone in creating the phenomenon of life, that the universe's complexity extends beyond our world to include other instances of self-organizing chemistry, other experiments in what matter can do when given the right conditions and enough time. The search continues, patient and methodical, observing one atmosphere after another, building knowledge, preparing for discovery. There's something almost surreal about the diversity of clouds the universe creates, about how the same basic physics, condensation of vapor into droplets or particles suspended in gas, produces wildly different results depending on temperature and pressure and chemical composition. On Earth, we have water clouds, ice clouds, clouds that rain liquid water or frozen crystals, clouds at different altitudes made of different forms of the same basic molecule, H2O. But Earth's clouds, as varied as they seem, represent only a tiny corner of the possibility space. They form in a narrow temperature range, roughly from 50 degrees C to 40 degrees, the range where water vapor, liquid water, and ice can all exist and transition between states. And they're made of one substance, water, because that's the volatile compound most abundant in Earth's atmosphere that can condense at temperatures we experience. But on other worlds, with different temperatures and different atmospheric compositions, clouds form from different materials, condense at different altitudes, create weather systems unlike anything we experience. On Venus, there are sulfuric acid clouds. On Jupiter, there are ammonia clouds, water clouds, and possibly clouds of ammonium hydrosulfide at different depths. On Saturn's moon Titan, there are methane clouds that rain liquid methane onto the surface. The universe's weather includes precipitation of materials that seem bizarre from our water-centric perspective. And on WASP 17b, a hot Jupiter 1300 light-years away, James Webb detected something unprecedented in October 2023. Clouds made of quartz crystals, pure silica nanocrystals, SiO2, floating in the planet's atmosphere, condensing directly from gas at temperatures around 2700 degrees. Let me explain how extraordinary this is, because quartz on Earth is a solid mineral, the second most abundant mineral in Earth's continental crust, found in rocks and sand and crystals, stable and unchanging except over geological timescales. When you hold a quartz crystal, you're holding silicon and oxygen atoms, arranged in a specific crystalline structure, bonded together in a tetrahedral pattern that makes quartz hard and chemically stable. But on WASP 17b, quartz isn't a ground mineral. It's a cloud component, tiny nanocrystals forming high in the atmosphere from gaseous silicon and oxygen, condensing the way water vapor condenses into water droplets on Earth, except at temperatures that would vaporize lead, that would melt rock, that are far beyond anything we'd call normal conditions for cloud formation. The physics works like this. WASP 17b is a very hot planet, orbiting very close to its star, with dayside temperatures exceeding 3000 degrees. At those temperatures, silicon-containing compounds can exist as gases: silica vapor, silicon monoxide, various silicon-oxygen compounds in gaseous form, floating around in the atmosphere mixed with hydrogen and other gases. As the atmospheric gas circulates, rising on the hot day side, flowing toward the cooler night side, descending and returning, it cools. And when it cools below about 2700 degrees, silica vapor reaches its saturation point and begins to condense, just like water vapor condenses into clouds when air cools below the dew point. But instead of water droplets, you get silica nanocrystals, tiny grains of pure quartz, perhaps tens to hundreds of nanometers across, forming in vast quantities at specific altitudes where the temperature is just right for condensation. These crystals are so small they remain suspended in the atmosphere, held aloft by atmospheric turbulence and updrafts, forming clouds or hazes that affect how light passes through the atmosphere and how the planet appears in observations. Webb detected these quartz clouds through spectroscopy, looking at how starlight is absorbed or scattered as it passes through WASP 17b's atmosphere during transit. Different cloud compositions scatter light differently. The wavelength dependence of scattering, the specific absorption features, the overall opacity at various wavelengths all provide clues about what the clouds are made of. And the data for WASP 17b matched pure silica, SiO2, better than any other cloud composition astronomers tested. This was the first time a specific cloud composition had been identified on an exoplanet. The first time we could say, definitively, this planet has clouds made of this specific material, rather than just inferring that clouds are present without knowing their composition. It's a level of detail in exoplanet characterization that seemed impossible just a few years ago, requiring extraordinary precision in spectroscopic measurements and sophisticated modeling of atmospheric processes. And quartz clouds have implications for the planet's atmospheric dynamics, its circulation patterns, its heat transport. Clouds affect how energy moves through an atmosphere. They reflect sunlight. They absorb infrared radiation. They release latent heat when they condense. They modify temperature, structure, and wind patterns. Understanding cloud composition is crucial for understanding how hot Jupiters work, how they transport heat from day side to night side, how their atmospheres respond to intense stellar radiation. On WASPA 17b, the quartz clouds probably form in regions where gas is cooling, perhaps on the night side, or at high altitudes, or in updrafts where adiabatic cooling drops the temperature below the silica condensation point. The crystals form, grow, perhaps fall, to lower, hotter altitudes where they evaporate back into gas, recycling silica through the atmosphere in a cycle analogous to Earth's water cycle, but occurring at temperatures where rock is soft and metals can melt. Imagine standing on WASP 17b. If you could, if you had a heat-resistant platform floating at the right altitude, if you could somehow survive in that infernal environment. Above you, the sky would glow from thermal emission, the atmosphere itself radiating in the infrared from its tremendous heat. The star would be enormous, filling much of the sky if you were on the day side. And around you, glittering in that strange light, would be clouds of crystalline sand, nanoparticles of pure quartz suspended in the thick atmosphere, forming hazes that would catch and scatter light in ways unlike any clouds on Earth. The crystals would be too small to see individually. Nanometer-scale particles are far below the resolution of human vision. But collectively, as clouds or hazes, they might create a shimmering effect, a subtle iridescence as light scatters off countless tiny crystals with similar sizes and shapes. Or maybe they just appear as haze, a subtle opacity that dims the star, creates a diffuse glow, affects visibility in ways that would seem odd and alien compared to our experience with water-based weather. And the weather on WASP 17b would be extreme even beyond the quartz clouds. The planet is tidally locked, always showing the same face to its star, creating permanent day and night hemispheres with a temperature difference of thousands of degrees. Winds blow from day to night at thousands of miles per hour, transporting heat, mixing atmospheric gases, carrying clouds of vaporized minerals from one hemisphere to another. The atmospheric circulation is continuous, powerful, global, driven by that enormous temperature gradient. Clouds form and evaporate in this circulation, condensing in cooler regions, evaporating in hotter regions, participating in the heat transport, affecting the temperature structure. The quartz clouds might be just one component. There could be other clouds at different altitudes, made of different materials that condense at different temperatures. Iron clouds, perhaps, or clouds of aluminum oxide, or other metal-containing compounds that can exist as gases at these extreme temperatures, but condense when cooled slightly. The atmosphere might have layers of different cloud types, each at altitudes where their specific condensation temperature is reached, creating a stratified structure similar to how Earth's atmosphere has different cloud types at different altitudes: low cumulus, middle altitude, alto stratus, high cirrus, each forming under different conditions and made of different forms of water. But on WASP 17b, instead of water in different phases, you'd have different minerals condensing at different altitudes, different materials creating different cloud layers, each with its own optical properties and dynamical effects. It would be weather, in a sense, changing conditions, evolving cloud patterns, variations in atmospheric properties over time and space, but weather unlike anything Earth experiences, operating under physical conditions completely outside our everyday experience. And Webb can detect this, can identify the specific cloud composition across 1,300 light years, can tell us that those clouds are made of quartz based on how they affect starlight passing through the atmosphere. That's remarkable when you think about it, that we can do mineralogy on alien worlds, that we can identify specific crystalline structures in clouds suspended in atmospheres we'll never visit, that we can understand chemical and physical processes occurring in environments completely different from anything on Earth. This capability matters for more than just satisfying curiosity about exotic weather. Understanding clouds on hot Jupiters helps us understand atmospheric physics in general, helps us model how energy transport works in thick atmospheres, helps us develop theories that can then be applied to other planets, including potentially habitable ones, where cloud properties might affect surface temperatures and climate habitability. Clouds affect climate profoundly. On Earth, cloud feedbacks are one of the major uncertainties in climate models. Will warming create more high clouds that trap heat or more low clouds that reflect sunlight? How will cloud properties change as the climate changes? These questions are difficult because clouds are complex, involving microphysics of droplet formation, turbulence, convection, radiation, phase changes, all interacting in complicated ways. Studying clouds on exoplanets, where conditions are different but physics is the same, provides additional test cases, additional constraints on our theories, additional examples of how clouds form and evolve under various conditions. WASP-17b's quartz clouds teach us about condensation physics at high temperatures, about how nanocrystals form from vapor, about how mineral clouds affect atmospheric opacity and heat transport. And that knowledge feeds back into our understanding of atmospheric physics generally, improving models that can be applied to many planets, including Earth. Science often works this way. Studying extreme cases illuminates general principles. Analyzing exotic examples clarifies fundamental physics. Investigating the unusual helps us understand the typical. There's also something aesthetically appealing about quartz clouds, about the idea of crystalline sand floating in alien skies, about clouds made of the same material as the sand on a beach or the crystals in a geode, but formed at temperatures that would melt metal. It's a reminder that minerals we think of as solid, stable, permanent, rock, quartz, silicates, can exist in different states under different conditions. That matter is more flexible than our everyday experience suggests. On Earth, in normal conditions, quartz is solid, hard, unchanging except through mechanical erosion or chemical weathering over long timescales. But heat it to a few thousand degrees, and it becomes vapor, molecules floating freely, mixed with atmospheric gases. Cool that vapor slightly, and it condenses into crystals, tiny perfect lattices of silicon and oxygen, forming spontaneously from the gas phase, organizing themselves into the lowest energy crystalline structure, creating nanoparticles that then float in the atmosphere until conditions change again. It's the same material, SiO2, silicon dioxide, quartz, but in a completely different context, behaving in completely different ways, existing in a state that would seem impossible from our terrestrial perspective. But that's perfectly natural given the conditions on WASP-17b. The universe constantly reminds us that our experience is limited, that what seems normal or natural or inevitable is actually context-dependent, specific to the particular conditions we happen to inhabit. We think of clouds as water because Earth's temperature range makes water clouds natural. But the universe makes clouds from whatever materials can condense at local temperatures. Water on Earth, ammonia on Jupiter, methane on Titan, sulfuric acid on Venus, quartz on WASP-17b, iron vapor on even hotter planets, exotic compounds. We haven't yet identified on others. Each planet is a variation on the theme of atmosphere with condensable volatiles creating clouds, but the specific implementation depends on local conditions, available chemistry, temperature, and pressure profiles. And each one teaches us something about that general theme, about how atmospheres work, about what's universal and what's contingent in atmospheric physics. WASP-17b with its quartz clouds is one such lesson, one variation on the theme, one example of how nature implements weather under extreme conditions. And the fact that we can identify those clouds' composition, that we can do detailed atmospheric chemistry on a planet 1,300 light years away, that we can learn about crystalline silica forming in an alien atmosphere. That's a testament to human ingenuity, to the power of spectroscopy, to what's possible when we build sophisticated instruments and think carefully about what signatures different phenomena would produce in the data. Rest now, perhaps marveling at the diversity of planetary environments, at how the same basic physical principles produce wildly different outcomes depending on initial conditions, at how the universe fills the possibility space of planetary configurations with examples ranging from the familiar to the exotic to the almost unimaginable. WASP-17b continues its orbit, its quartz clouds forming and evaporating in eternal cycles, its atmosphere circulating in patterns driven by the tremendous temperature contrast between its eternal day and eternal night, its weather proceeding according to physical laws that operate everywhere in the universe, creating phenomena we're only now learning to observe and understand. Weather is something we experience constantly on Earth, something so familiar it's almost mundane. Clouds forming and dissipating, wind blowing from one direction, then another, rain falling, then stopping, temperatures rising and falling in daily and seasonal cycles. We have forecasts predicting what weather will do hours or days in advance, satellite images showing cloud patterns across entire continents, sophisticated models simulating atmospheric dynamics in detail. But until recently, we had weather forecasts for only one planet, Earth. We had some observations of weather on other solar system bodies, Jupiter's great red spot, the changing appearance of Mars's polar caps, seasonal variations on Saturn, but nothing like the detailed, comprehensive weather monitoring we have for Earth. We couldn't map wind patterns or track storm systems or measure temperature variations across their surfaces with the precision we take for granted for our own world. And for exoplanets, for planets orbiting other stars, we could barely detect that they had atmospheres at all, let alone map their weather patterns, track their circulation, create genuine meteorological observations of distant worlds. That changed in April 2024, when James Webb released the first comprehensive weather map of a hot Jupiter, WASP-43b, a planet roughly twice Jupiter's mass orbiting a star 280 light-years away, completing one orbit every 19.5 hours. Webb's observations mapped temperature, wind patterns, and cloud distribution across the planet's entire surface, creating a three-dimensional picture of an alien world's weather, the first genuine meteorological portrait of an exoplanet. Let me describe what Webb found, because the weather on WASP 43b is both familiar in its basic physics and utterly alien in its specifics, operating under conditions that push atmospheric dynamics to extremes far beyond anything we experience on Earth. The planet is tidally locked, like the moon is to Earth, always showing the same hemisphere toward its star. This creates a permanent day side and a permanent night side, with no rotation to mix conditions, no day-night cycle to average out temperatures. The day side receives continuous, intense stellar radiation, heating to about 2300 degrees Celsius. The night side receives no direct starlight, cooling to around 2100 degrees, still scorching by Earth standards, hot enough to melt some metals, but much cooler than the day side. That 1200 degree temperature difference drives powerful atmospheric circulation. Hot air rises on the day side, flows toward the night side at high altitudes, cools and descends, then returns to the day side at lower altitudes, creating a global circulation pattern similar to Earth's Hadley cells, but wrapping around the entire planet and operating at much higher velocities. And the winds are staggering. Webb measured wind speeds exceeding 5,000 miles per hour at the equator, flowing from the day side to the night side. For comparison, Earth's jet streams reach maybe 200 to 300 mph at most. Hurricane wind speeds top out around 200 mph for the strongest storms. WASP 43b's winds are more than 20 times faster, approaching Mach 7, fast enough to circle Earth in under 5 hours if they somehow existed here. These winds transport heat from day side to night side, mixing atmospheric gases, preventing the night side from cooling to the extreme temperatures it would reach without heat transport. They're fast enough that they shift the hottest point on the planet slightly eastward of the substellar point, the location directly beneath the star, because hot air is blown downstream before it can fully radiate its heat away. And the clouds, Webb detected thick clouds on the night side but clear skies on the day side, a pattern that makes sense given the temperature difference. On the hot day side, any condensable materials remain as gases. Temperatures are too high for cloud particles to form and survive. But on the cooler night side, various compounds can condense into clouds or hazes, creating opacity that affects how heat escapes from that hemisphere. The specific composition of those night-side clouds remains uncertain. Possible candidates include silicate clouds, metal vapor clouds, clouds of various sulfur or phosphorus compounds. Different materials condense at different temperatures, and WASP 43b's night side temperature allows various candidates. More detailed spectroscopic observations might identify specific cloud components, but for now we know clouds are present without knowing precisely what they're made of. This day-night cloud asymmetry has implications for the planet's heat budget, its energy balance, how efficiently it radiates energy away compared to how much energy it receives from the star. Clouds affect radiation. They can reflect sunlight, not relevant on the dark night side, and they can trap infrared radiation, very relevant, affecting how much heat escapes to space. Understanding cloud distribution is necessary for understanding the planet's overall energy balance and why it has the temperature it does. Webb also mapped how temperature varies with altitude, creating a three-dimensional thermal structure of the atmosphere. Temperature generally decreases with altitude on the day side. hotter at depth where the atmosphere is denser and pressure is higher, cooler at high altitude where gas is thinner. But the profile isn't uniform, showing features that suggest various processes: radiative heating and cooling, adiabatic temperature changes from rising and sinking gas, possibly temperature inversions where temperature increases with altitude in certain regions due to absorption of starlight by atmospheric molecules or haze particles. This three-dimensional mapping is extraordinary when you consider the technique. Webb didn't directly image the planet. It's far too faint and too close to its bright star to be photographed as a resolved object. Instead, Webb observed the combined light of the star and planet, watching how the total brightness changed as the planet orbited the star and showed different hemispheres toward us. When the day side is facing Earth, we see more infrared light because the day side is hot and glowing thermally. When the night side faces us, we see less infrared light because it's cooler. As the planet orbits, different regions come into view, and the brightness variations tell us about temperature distribution across the planet's surface. By observing at multiple wavelengths, astronomers can map not just total temperature, but temperature at different altitudes, since different wavelengths probe different atmospheric depths, and can infer wind speeds from how the hottest regions are shifted from where they'd be without wind transport. It's indirect, requiring sophisticated modeling to interpret the observations, but it works, producing genuine weather maps that show temperature and wind patterns and cloud distribution across an alien world. And these aren't static maps. They represent average conditions, typical weather patterns, the mean state of an atmosphere that's constantly in motion, constantly circulating, constantly adjusting to the forcing from stellar radiation, and the constraint of global-scale fluid dynamics. Does WASP 43b have storms in the sense of localized, temporary disturbances like Earth's hurricanes or thunderstorms? Probably not, at least not in the same way. The circulation is likely more steady state, continuously flowing in response to the permanent day-night temperature contrast, rather than forming discrete storm systems that grow and decay. But there might be variability, turbulence, eddies, instabilities in the flow that create temporary features, regions where conditions deviate from the average. Longer-term monitoring might reveal such variations, showing whether the weather is truly steady or exhibits fluctuations over time. That's harder to measure. It requires many observations over long periods, accumulating data to characterize temporal variability, distinguishing long-term changes from measurement noise or systematic effects. But it's possible in principle, and future observations might provide that temporal dimension, telling us whether hot Jupiter weather is static or dynamic on short timescales. The achievement here isn't just the specific findings about WASP 43b, though those are scientifically valuable. It's the demonstration that we can do comprehensive meteorology on exoplanets, that we can map their weather in meaningful detail, that we have the observational capabilities and analytical techniques to study alien atmospheres with the kind of thoroughness previously possible only for solar system planets. This opens a new era in exoplanet characterization. We're no longer limited to measuring average properties, mean temperature, overall composition, crude estimates of atmospheric structure. We can map spatial variations, track circulation patterns, identify day-night contrasts, detect clouds in specific regions, create genuine meteorological portraits that show how these atmospheres actually behave. And as techniques improve and more planets are observed, we'll build up a comparative meteorology of exoplanets, understanding how atmospheric circulation works under different conditions, different temperatures, different rotation rates, different atmospheric compositions, different stellar radiation levels. Each planet is an experiment in fluid dynamics, an example of how atmospheres respond to specific forcing and constraints, teaching us about the general principles governing planetary weather. Earth's atmosphere is complex, with continents and oceans and topography and life all affecting circulation in ways that make it difficult to isolate fundamental processes. But hot Jupiters like WASP-43b are simpler in some ways. No continents, no oceans, no surface boundary layer, just a thick atmosphere responding to stellar heating and rotation. They're cleaner test cases, easier to model, providing examples where theory can be tested without as many confounding factors. So studying WASP-43b's weather helps us understand atmospheric dynamics generally, including on Earth, by providing a different example, a different parameter regime, additional constraints on theories of how atmospheres work. It's comparative planetology in action, using the diversity of exoplanets to understand the principles governing all planets. And there's something awe-inspiring about the fact that we can do this, that we can measure wind speeds and temperature patterns and cloud distributions on a planet 280 light-years away, that we can map weather on a world we'll never visit, that we can do meteorology across interstellar distances using nothing but careful measurements of infrared light and sophisticated modeling of atmospheric processes. The universe is knowable, measurable, understandable, even across distances that seem impossibly large. Light carries information, and if we're clever enough about how we observe it and analyze it, we can decode that information, learning about conditions in places we can't reach, measuring properties of objects we can't touch, mapping weather on worlds separated from us by trillions upon trillions of miles. WASP-43b's weather continues, indifferent to our observations. Winds blowing at thousands of miles per hour, heat flowing from dayside to nightside, clouds forming and dissipating, the entire atmosphere in constant motion, driven by physics that's universal, following laws that operate everywhere in the cosmos. And we're here, watching from 280 light-years away, learning about that distant weather, adding another world to our growing catalog of known atmospheres. Rest now, knowing that weather happens throughout the universe, that atmospheric circulation is a universal phenomenon wherever planets have atmospheres and energy gradients, that the winds blow on countless worlds following the same fluid dynamics that shape Earth's weather, but producing outcomes as diverse as the planets themselves. The map of WASP-43b's weather is archived now, data captured and analyzed. A meteorological portrait of an alien world preserved for future study, teaching us about atmospheric physics, demonstrating what's possible in exoplanet characterization, showing us weather as it happens on a world utterly unlike our own. Sometimes nature creates objects that don't fit into our taxonomies, that exist in the fuzzy boundaries between categories we've carefully defined, that challenge our definitions and force us to reconsider whether our classifications are natural features of the universe or merely convenient human constructs. Stars are objects that fuse hydrogen in their cores, generating energy through nuclear reactions, shining by their own light. Planets are objects that orbit stars, formed in circumstellar disks, generally not massive enough to fuse hydrogen. Brown dwarfs occupy the middle ground, too massive to be planets, typically more than about 13 Jupiter masses, but not massive enough to sustain stable hydrogen fusion, less than about 75 Jupiter masses, glowing from residual heat left over from their formation, but not truly shining like stars. These definitions seem clear enough until you encounter objects that blur the boundaries, that have properties suggesting one category, but formation mechanisms suggesting another, that exist in regimes where multiple processes overlap and distinctions become arbitrary. And then there are the jumbos. Jumbos, Jupiter mass binary objects, were discovered by James Webb in the Orion Nebula in October 2023, and they immediately became one of the most puzzling findings in recent astronomy. Webb found over 40 pairs of these objects, each pair consisting of two Jupiter-sized bodies gravitationally bound to each other, orbiting their common center of mass, drifting through space together with no parent star nearby. Let me emphasize what makes this so strange. These are planet-sized objects, roughly Jupiter's mass, somewhere between 0.6 and 13 Jupiter masses, based on preliminary estimates. But they're not orbiting stars. They're free-floating, wandering through the Orion Nebula in gravitationally bound pairs, orphaned worlds without stellar parents. And they're not alone. They're in pairs, orbiting each other at separations of roughly 25,400 astronomical units, distances comparable to the outer reaches of our solar system. They're binary systems of planet mass objects, and nobody predicted that such things should exist in such abundance. Individual free-floating planets, called rogue planets, have been discussed for decades. Theories predict they should form in protoplanetary disks, just like normal planets, but then get ejected through gravitational interactions with other planets, ending up wandering through interstellar space, untethered to any star. Simulations of planetary system formation suggest that ejection is fairly common. Early planetary systems are dynamically unstable, with planets gravitationally scattering each other, sometimes resulting in some being thrown outward at escape velocity. So rogue planets should exist, and we've probably detected some, though distinguishing between genuine rogue planets and very low-mass brown dwarfs is observationally challenging, since both are faint objects not orbiting stars. But individual rogues make sense theoretically, planets that formed normally but got unlucky and were ejected. But rogue planet pairs? Binary systems of planet mass objects? That's much harder to explain. If planets formed in a disk around a star and then were ejected, the ejection process would almost certainly separate them. The gravitational interactions causing ejection are violent and chaotic, producing random outcomes, and the probability of ejecting two planets together while maintaining their mutual orbit seems vanishingly small. So if jumbos didn't form as planets and get ejected together, how did they form? Several possibilities are being discussed, none entirely satisfactory. One idea is that they formed like binary stars, through gravitational collapse and fragmentation of gas clouds. Binary stars are common. Maybe half of all stars are in binary or multiple systems. forming when a collapsing cloud fragments into two or more cores that become separate stars orbiting each other. Maybe jumbos formed the same way, but the collapsing clouds happen to be less massive, producing Jupiter mass objects instead of stars. But this raises theoretical problems. Cloud fragmentation doesn't work efficiently at very low masses. There are minimum mass thresholds below which clouds don't fragment, below which collapse produces a single object rather than multiples. Standard star formation theory suggests that Jupiter mass objects should form through different mechanisms than stars, and shouldn't naturally produce binaries through fragmentation. Moreover, if jumbos formed like stars, they'd technically be very low-mass brown dwarfs, not planets at all, even though their masses are in the planetary range. The definition of planet versus brown dwarf is sometimes based on formation mechanism. Planets form in disks, brown dwarfs form through cloud collapse, rather than purely on mass, so calling them jumbos rather than ultra-low mass brown dwarf binaries might be more appropriate if they formed through collapse. Another possibility involves disk fragmentation. Some massive protostellar disks might be gravitationally unstable, fragmenting directly into multiple objects rather than slowly accreting into planets. If two such objects formed in the same unstable disk and were then ejected together, they might remain gravitationally bound as a binary, becoming a jumbo pair. But this still requires the ejection process to preserve their binary nature, and it requires conditions allowing disk fragmentation at very low masses, and it needs to happen often enough to produce 40-plus pairs just in the relatively small region of the Orion Nebula that Webb surveyed. A more exotic possibility is that jumbos are fragments of stars that never fully formed, products of cloud cores that collapsed but somehow split into multiple low-mass pieces before they could complete star formation. Or maybe they're remnants of disrupted systems, pieces of planetary systems that were torn apart by close encounters with passing stars, with the planets somehow remaining bound to each other while losing their stellar parent. None of these explanations is fully satisfying. All require special conditions or unusual circumstances or processes that aren't well understood. And the abundance of jumbos is troubling. Finding 40-plus pairs in one star-forming region suggests they're not rare anomalies, but a significant population, a common outcome of whatever formation process creates them. The Orion Nebula is one of the nearest and most studied star-forming regions, only about 1/350 light-years away, actively forming stars right now. It's been surveyed countless times with various telescopes, but Webb's infrared sensitivity and resolution revealed these jumbo pairs for the first time, showing faint objects that previous observations missed or couldn't resolve clearly. And if the Orion Nebula contains dozens of jumbos, how many might there be throughout the galaxy? Extrapolating from this one region to all star-forming regions suggests there could be millions or billions of jumbos wandering through the Milky Way. An entire population of planet-mass binary systems drifting through interstellar space, contributing to the galaxy's dark population of faint objects that don't shine brightly, but add to the overall mass budget. The masses are uncertain. Estimating masses for faint objects without knowing their ages or compositions precisely is difficult. The range of 0.6 to 13 Jupiter masses is preliminary, based on luminosity and temperature estimates and assumptions about evolutionary models. More detailed follow-up observations might refine these mass estimates, might show that some jumbos are slightly more massive than Jupiter, hence possibly very low-mass brown dwarfs, while others are less massive, hence definitely planets if they formed in disks, but ambiguous if they formed through collapse. And the formation question remains open. Maybe different jumbo pairs formed through different mechanisms, some through disk fragmentation, some through cloud collapse, some through capture or exchange interactions in dense stellar environments. Nature doesn't always use a single pathway. Multiple formation channels might contribute to the population. But whatever the explanation, jumbos are real, observed, numerous, and puzzling. They exist in a regime where our theoretical understanding is incomplete, where formation processes overlap, where the boundaries between planets and brown dwarfs blur. They're reminders that the universe is richer and more diverse than our theories predict, that nature fills niches we didn't know existed, that classification schemes are human impositions on a continuous distribution of properties rather than reflections of sharp natural boundaries. There's something almost philosophical about jumbos, about these orphaned binary planets, or paired dwarf stars, or whatever they are, wandering through space together, gravitationally bound to each other, but not to any star, existing in a configuration that challenges our definitions and taxonomy. Are they planets? They have planetary masses. But do planets exist without stars? If they formed through cloud collapse like stars, are they tiny stars rather than planets? Does formation mechanism or mass determine what something is? These questions matter for more than just terminology. Understanding what jumbos are and how they formed is important for understanding star formation, planet formation, the mass distribution of objects in the galaxy, the efficiency of various formation processes. And it reminds us that nature doesn't necessarily organize itself according to our categories, that real objects don't always fit neatly into our classification boxes, that the universe is messier and more complicated than our theoretical frameworks sometimes suggest. And maybe that's appropriate. Maybe the universe should surprise us, should create phenomena we didn't predict, should blur the boundaries we've drawn between categories. It keeps us humble, keeps us learning, keeps us revising and improving our theories, rather than assuming we've figured everything out. The jumbos drift through the Orion Nebula, orbiting each other in their binary dance, unaware of and unconcerned with our attempts to classify them, to explain their existence, to fit them into our theoretical frameworks. They simply are. Objects following physical laws, products of some formation process, examples of what gravity and thermodynamics can create given the right conditions and enough time. And we're here, observing them with our sophisticated infrared telescope, documenting their existence, measuring their properties, puzzling over their origins, adding them to our catalog of cosmic phenomena that need explanation. Science advances through such puzzles, through discovering things that don't fit existing theories, through being forced to expand our understanding, to accommodate new observations. Jumbos might be a minor curiosity, an interesting footnote in the catalog of celestial objects, or they might be a significant population that changes our understanding of how low-mass objects form and how common rogue worlds are. Time and additional observations will tell. But for now, they're a mystery, a puzzle, a reminder that the universe still has surprises for us, still creates objects we didn't predict, still operates in ways that challenge our theoretical frameworks and force us to think more carefully about how nature works. Rest now, knowing that the cosmos is full of strange objects existing in boundary regions between our categories, following physical laws but producing outcomes we didn't anticipate, filling the galaxy with diversity that exceeds our theoretical predictions. The jumbos continue their orbits, paired wanderers drifting through space, bound to each other if to nothing else. Examples of nature's creativity, products of formation processes we're still learning to understand. There's a particular satisfaction in scientific theories that work, in models that successfully predict what observations will find, in frameworks that explain diverse phenomena with elegant simplicity. The standard cosmological model, called LCDM for lambda cold dark matter, has been remarkably successful in this regard, explaining the cosmic microwave background, the large-scale structure of the universe, the abundance of light elements, galaxy formation timelines, the acceleration of cosmic expansion. It fits countless observations, from the smallest scales accessible to our instruments to the largest structures spanning billions of light years. But the model makes specific predictions about how galaxies should form and evolve, about how quickly they should build up mass, about how large and luminous they should be at different cosmic epochs. And those predictions work beautifully for the nearby universe, for galaxies we observe today, or in the relatively recent past few billion years. The model says galaxies should grow hierarchically, small galaxies forming first, then merging to build larger galaxies over time, with the most massive galaxies appearing relatively late in cosmic history, after billions of years of gradual accumulation. This timeline seems solid, well established, supported by observations of the universe at various epochs, showing that, indeed, large galaxies are more common now than they were billions of years ago, that the universe has been building larger structures over time as predicted. And then James Webb looked at the earliest cosmic epochs, at galaxies forming in the first 500–700 million years after the Big Bang, and found galaxies that shouldn't exist according to those predictions, galaxies that are too massive, too bright, too evolved for their age, galaxies that formed too quickly, built up too much mass too fast, developed too much structure too early, galaxies that astronomers, with a mixture of bewilderment and amusement, nicknamed universe breakers. 6 such galaxies were among the first identified, officially known as candidates from deep field surveys, but immediately recognized as problematic for standard models. They appeared extraordinarily bright at redshifts corresponding to 500 to 700 million years after the Big Bang, with luminosities suggesting stellar masses of tens of billions of solar masses, comparable to the Milky Way's mass, but existing when the universe was less than 5% of its current age. Let me emphasize the problem. According to LCDM models, galaxies this massive shouldn't exist this early. There hasn't been enough time for star formation to build up tens of billions of solar masses, for galaxies to merge and grow to these sizes, for the hierarchical assembly process to produce such large structures. It's like finding a full-grown tree in a forest that was planted last week. Something's not adding up. The initial observations came from Webb's near-infrared camera, identifying extremely red objects at high redshifts. Follow-up spectroscopy confirmed they were genuinely distant, not just nearby dusty galaxies masquerading as high redshift objects. And photometric analysis, measuring their brightness at multiple wavelengths, suggested they were massive and luminous, far more than should exist at those epochs. Several possibilities might explain these universe breakers, ranging from observational systematics to genuine new physics. First, maybe the stellar mass estimates are wrong. Converting observed luminosity to stellar mass requires assumptions about the stellar population, how old the stars are, what their metallicity is, whether there are lots of massive young stars or mostly older populations. If these galaxies have unusual stellar populations dominated by very massive stars, for instance, which are intrinsically brighter, they might appear more massive than they actually are. The luminosity would be real, but the inferred mass would be overestimated. Second, maybe active galactic nuclei, supermassive black holes consuming gas and shining brightly, are contributing significant light, making the galaxies appear more luminous than they would be from stars alone. If AGN contamination is significant, the stellar mass would be lower than estimated from total luminosity, potentially bringing these galaxies back into consistency with models. Third, maybe there's dust reddening affecting the photometry in ways that bias mass estimates. Dust absorbs blue light and re-emits it in the infrared, which can create confusion when trying to determine a galaxy's stellar population from limited photometric data. More detailed spectroscopy might reveal that dust is playing a larger role than initially thought. But fourth, and most intriguingly, maybe these galaxies are genuinely massive, genuinely anomalous, genuinely challenging our models of early galaxy formation. Maybe the early universe was more efficient at converting gas into stars than we thought. Maybe star formation proceeded more rapidly in those first few 100 million years, building up stellar mass faster than our current models predict. Why might that be? Several physical mechanisms could enhance early star formation efficiency. The early universe had simpler chemistry, mostly hydrogen and helium, very few heavy elements. This affects cooling rates, fragmentation properties, how efficiently gas clouds can collapse. Maybe pristine gas behaves differently than metal-enriched gas, allowing more efficient star formation under early conditions. Or maybe supermassive black holes formed earlier and more massive than we thought, and their presence in galactic centers somehow triggered enhanced star formation in surrounding gas. Black hole activity and star formation are connected through various feedback mechanisms, and maybe those feedbacks operated differently in the early universe. Or maybe dark matter halos assembled more efficiently than standard models predict, creating deeper gravitational wells earlier, allowing gas to accumulate and form stars more rapidly in overdense regions that were destined to become galaxy clusters. Or maybe the initial density fluctuations left over from the Big Bang, the seeds from which all structure grew, were slightly different than we've modeled, with more power at certain scales, creating more massive structures earlier than expected. Each of these possibilities would require modifying the standard cosmological model, adjusting parameters or adding new physics to match observations. And that's fine. Models are tools, approximations, frameworks that need updating when new data demands it. Science advances by finding discrepancies between predictions and observations, then revising theories to accommodate the new information. The universe breakers represent such a discrepancy. They're not impossible. They exist, we observe them. They're real galaxies at real distances. But they're unexpected, challenging, forcing theorists to reconsider assumptions about early galaxy formation efficiency, about how quickly structure could build up in the first billion years, about whether LCDM in its current form captures all relevant physics or needs refinement. And it's not just those 6 initial candidates. As Webb observations continue, more early massive galaxies are being found, building up a population of objects that are systematically more luminous and apparently more massive than predictions suggested. It's becoming clear that this isn't just a few weird outliers, but potentially a systematic difference between models and reality, a genuine revision needed in our understanding of cosmic dawn. Some astronomers are exploring modifications to star formation efficiency in the early universe, adjusting how much gas gets converted into stars and on what timescales. Others are reconsidering dark matter properties or initial conditions, or the role of black holes in early galaxies. Still others are scrutinizing the observational methods, checking whether systematic errors might be biasing mass estimates in ways that make these galaxies appear more anomalous than they actually are. This is science at the frontier, where observations have outpaced theory, where we know what we're seeing but don't fully understand how to explain it within existing frameworks. It's uncomfortable but exciting. Uncomfortable because it means our best models are incomplete. Exciting because it means there's new physics to discover, new understanding to develop, new insights waiting to emerge from the collision between prediction and observation. The name universe breakers is somewhat tongue-in-cheek. These galaxies don't literally break the universe or violate physical laws, but they do break our models, or at least strain them significantly, pushing against the limits of what LCDM predicts and suggesting that revisions are needed. And there's something humbling about that, about being reminded that even our most successful theories have limits, that the universe is under no obligation to conform to our models, that nature is richer and more complex than our simplified frameworks capture. We built LCDM from decades of observations of the relatively nearby universe, from measurements of the CMB, from theoretical considerations about what kinds of particles and fields might exist, and it works brilliantly for explaining most of what we see. But the earliest epochs, cosmic dawn, reionization, the first billion years, were observationally inaccessible until recently. We extrapolated our models backward in time, predicted what those early epochs should look like, then waited for telescopes capable of testing those predictions. And now Webb has provided those tests, and the predictions aren't perfectly matching observations. And we're learning that the early universe was more complex, more efficient at building structure, more productive at forming stars than our extrapolations suggested. This is how science progresses, not through perfect predictions confirmed endlessly, but through surprises, through discrepancies, through observations that don't quite fit and force reconsideration of assumptions. The universe breakers are such a surprise, a gift from the cosmos that's forcing cosmology to evolve, to refine its models, to develop richer theories that can accommodate both the successes of LCDM in the late universe and these unexpected observations of the early universe. And perhaps in retrospect, we shouldn't be entirely surprised. The early universe was a different place, denser, hotter, more uniform, simpler in chemistry, but perhaps richer in dynamical processes. Extrapolating late universe physics backward across 13 billion years assumes that processes scaled smoothly, that efficiencies didn't change dramatically, that no new phenomena dominated at early times. But maybe that assumption was too simple. Maybe the early universe had its own character, its own dynamics, its own ways of building structure that differed from later epochs. The universe breakers are teaching us about that early character, about how the infant cosmos operated, about the pathways by which the first large galaxies formed. They're data points constraining new models, observations that will shape the next generation of cosmological theory, evidence that will refine our understanding of cosmic history. And there will be more. Webb is just beginning its mission, with many years of observations ahead. More deep fields will be surveyed, more early galaxies discovered, more detailed measurements obtained. The sample of universe breakers will grow. Their properties will be characterized more precisely, and the statistical patterns will become clearer. Eventually, theorists will develop models that explain these galaxies naturally, that predict their properties and abundances, that reconcile them with the successful predictions LCDM makes for later cosmic epochs. That's the trajectory of science: observation, surprise, theoretical development, eventual synthesis where new models explain both old and new data within a unified framework. We're currently in the surprise phase regarding universe breakers, where observations have revealed something unexpected, and theorists are scrambling to develop explanations. But eventually, we'll reach synthesis, where a refined cosmological model will naturally predict these early massive galaxies as an expected outcome of early structure formation under correctly modeled physics. And when we reach that synthesis, our understanding of cosmic history will be richer, more complete, more accurate than before. We'll know how galaxies really formed in the first billion years, what physical processes dominated, what efficiencies applied, how rapidly structure built up from initial conditions. The universe breakers will have broken our models in order to build better ones, forced revision in order to enable progress. So rest now, knowing that the universe continues to surprise us, that our theories, powerful as they are, remain works in progress, that observations continue to challenge our understanding and drive scientific advancement. The universe breakers exist in the early cosmos, massive and bright and puzzling, waiting for theorists to develop the frameworks that will explain them, that will integrate them into our cosmic story, that will reveal what they're teaching us about how the universe builds its structures. The early galaxies shine in Webb's images, ancient light carrying information about cosmic dawn, about star formation in the universe's youth, about how matter organized itself in those first few 100 million years. And we're here, interpreting that light, measuring those properties, learning from those observations, gradually constructing a more complete and accurate understanding of cosmic history. The universe breakers challenge us, inspire us, force us to think more carefully and deeply about early galaxy formation. And through that challenge, through that forced reconsideration of assumptions, science advances, understanding deepens. and our model of cosmic history becomes richer and more nuanced. There's a particular kind of violence in the universe that creates beauty from destruction, that takes the death of a star and transforms it into a cosmic recycling event that enriches the galaxy and seeds future generations of stars and planets. Supernovae are such events, the explosive deaths of massive stars, releasing more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime, blasting stellar material outward at thousands of miles per second, creating shock waves that heat gas to millions of degrees and forge new elements in the extreme conditions of the explosion itself. And what remains after a supernova is a supernova remnant, an expanding shell of ejected material, glowing from the energy of the explosion, visible for thousands of years as the debris gradually slows and dissipates into the interstellar medium. These remnants are among the most beautiful objects in the sky. Intricate filaments, delicate structures, complex shapes that reveal the physics of shock waves and magnetic fields and plasma instabilities, all painted in the characteristic colors of various elements heated to incandescence. Cassiopeia A is one such remnant, one of the youngest and best-studied supernovae in our galaxy. The explosion occurred about 340 years ago, as measured from Earth. The light from the explosion would have reached Earth around 1680, though apparently no one recorded seeing it, despite it being relatively nearby, at about 11,000 light-years distance. The progenitor star was massive, perhaps 15-20 times the Sun's mass, and when it exhausted its nuclear fuel, its core collapsed catastrophically, triggering a supernova explosion that blasted the star's outer layers into space. James Webb observed Cassiopeia A in extraordinary detail in July 2024, and among the many findings was the detection of surprisingly bright carbon monoxide emission, complex molecules surviving and even forming in the violent aftermath of a stellar explosion, in conditions that would seem to preclude any complex chemistry at all. Let me explain why this is remarkable. Because carbon monoxide seems simple, stable, a molecule we encounter commonly on Earth. CO is a byproduct of incomplete combustion, present in car exhaust, produced when organic materials burn without sufficient oxygen. It's toxic to humans but chemically unremarkable. Just a carbon atom bonded to an oxygen atom, one of the simplest molecules containing a heavy element. But in the context of a supernova remnant, CO shouldn't exist in any significant abundance. Supernova explosions heat material to billions of degrees, completely dissociating any molecules into atoms, or even ionizing the atoms themselves, stripping electrons away and creating a plasma of free nuclei and electrons. As the ejecta expands and cools, atoms can recombine, electrons reattaching to nuclei, but temperatures remain high enough that molecular formation should be suppressed, or at least very inefficient, for thousands of years after the explosion. Yet Webb detected substantial amounts of carbon monoxide in Cassiopeia A, glowing brightly in infrared emission, distributed through the expanding remnant in clumps and filaments. And this CO wasn't just surviving from before the explosion. It was forming now, being created in the supernova remnant through chemical reactions occurring in the cooling gas, even in the violent environment of an expanding shock wave. How is this possible? Several factors contribute. First, the supernova ejecta isn't uniform. It's clumpy, with denser regions and less dense regions, shock waves and relatively quiescent gas, hot zones and cooler pockets. In the denser, cooler regions, protected somewhat from the full violence of the explosion and the reverse shock waves, conditions can allow molecular formation even while overall temperatures remain high by terrestrial standards. Second, dust forms relatively early in supernova remnants, tiny grains of carbon or silicates condensing from the vapor as gas cools. These dust grains provide surfaces where atoms can meet and bond, catalyzing molecular formation in ways that would be inefficient in gas phase chemistry. A carbon atom and oxygen atom striking a dust grain might have their thermal energies absorbed by the grain, allowing them to bond and form CO, which then desorbs from the grain into the surrounding gas. Third, the elements produced in the supernova: carbon from helium burning, oxygen from carbon burning, various other products from the different burning stages and from the explosion itself, are freshly available, not locked up in existing molecules or compounds, ready to form new molecules as conditions allow. So carbon monoxide forms along with other simple molecules in the cooling supernova ejecta. And this CO emission, detected by Webb's infrared instruments, provides valuable information about the chemistry, temperature structure, density distribution, and dynamical state of the remnant. Different molecules emit at different wavelengths and under different conditions. So mapping molecular emission maps physical conditions tells us where gas is cool enough for molecules, where it's too hot, where it's dense enough for efficient formation, where it's too diffuse. But the broader significance is what this tells us about the cosmic recycling program, about how material from dead stars gets returned to the interstellar medium and eventually incorporated into new stars and planets. The carbon and oxygen in that CO will eventually, perhaps thousands of years from now, mix with interstellar gas, become part of a new molecular cloud, participate in new star formation, perhaps get incorporated into a protoplanetary disk, and eventually into a planet or even into living organisms. This is how the universe builds chemical complexity, how it enriches itself with heavy elements, generation after generation. The first stars were pure hydrogen and helium, unable to make rocky planets or complex chemistry or life. But they fused lighter elements into heavier ones, then exploded, scattering those heavy elements through space. The second generation of stars formed from slightly enriched gas produced even more heavy elements, exploded, enriched further. Each cycle adds to the cosmic abundance of carbon, oxygen, nitrogen, iron, all the elements necessary for complex chemistry. And molecular formation in supernova remnants is part of that cycle, the immediate step where freshly produced elements start combining into compounds, start exploring chemical space, start forming the molecules that will eventually contribute to new stellar systems. CO is just one example, one of the simpler molecules, but it represents the beginning of a process that leads to increasingly complex chemistry, eventually to organic molecules, to the chemical ingredients of life. Your body contains carbon and oxygen that were produced in stars, scattered by supernovae, incorporated into the molecular cloud that formed the solar system, eventually ending up in Earth and in you. The oxygen you breathe, the carbon in your DNA, the nitrogen in your proteins, all of it was made in stars and distributed by supernovae or stellar winds or other processes that return stellar material to the interstellar medium. And Cassiopeia A is that process in action, that cycle continuing, fresh stellar material being scattered, molecules forming even in the violent aftermath of explosion, the first steps of chemical enrichment proceeding in real time, or at least real time, as of 340 years ago when the explosion occurred, accounting for light travel time. Webb's detection of bright CO emission shows that this molecular formation is efficient, occurring throughout the remnant, producing substantial amounts of simple molecules despite the harsh environment. And if CO can form this efficiently, other molecules can too. More complex species, organic compounds, perhaps even the building blocks of biological molecules. Though that level of complexity probably requires later stages, calmer environments, more time for chemistry to explore its possibilities. But the foundation is being laid in Cassiopeia A, and in thousands of other supernova remnants throughout the galaxy. Each one is a source of chemical enrichment, a site where heavy elements are produced and distributed, where molecules form from freshly made atoms, where the cosmic cycle of stellar birth, life, death, and rebirth continues its endless progression. And there's something poetic about molecules forming in the debris of a stellar explosion, about order emerging from chaos, about chemistry proceeding even in violence, about the universe's persistent drive toward complexity. The supernova tried to destroy everything, blast it all apart, reduce the star to its component atoms, and scatter them across light years of space. And even in that destructive event, even in the expanding shockwave and the heated plasma, nature finds ways to build molecules, to create structure from the wreckage, to begin the process of recycling and renewal. It's a bit like a forest fire, destructive, violent, consuming everything in its path, but also clearing space for new growth, returning nutrients to soil, creating conditions where new life can flourish. Supernovae are cosmic forest fires, destroying stars but enriching the galaxy, creating space in dense regions while simultaneously providing the raw materials for new star formation, maintaining the cycle that keeps galaxies alive and evolving. Cassiopeia A will continue expanding, cooling, gradually fading as its energy dissipates. Eventually, tens of thousands of years from now, it will be indistinguishable from the background interstellar medium, its material completely mixed with surrounding gas, its energy fully radiated away. But the elements it produced and scattered will remain, incorporated into new clouds, new stars, new planets, new instances of complexity. And the CO molecules Webb detected, those specific molecular bonds between carbon and oxygen atoms in the Cassiopeia A remnant, they won't last. They'll be destroyed by radiation, dissociated by shock waves, broken apart by cosmic rays or UV photons. But the atoms will persist, cycling through various forms, participating in different chemical reactions, eventually forming different molecules, continuing the endless transformation of matter that characterizes the cosmos. You are made of atoms that have been through this cycle multiple times. Every heavy element in your body was forged in a star, scattered by some stellar death. Supernova or stellar wind or planetary nebula, mixed with interstellar gas, incorporated into new stars, perhaps scattered again, eventually ending up in the molecular cloud that formed our solar system, incorporated into Earth, cycled through geology and biology, and now temporarily arranged in the pattern that is you. The carbon in your cells might have been part of CO molecules in some ancient supernova remnant billions of years ago, before the sun formed, before Earth existed. Those molecules are long gone, destroyed, and reformed countless times, but the atoms persist, carrying with them a history we can only imagine. A journey through stars and nebulae and planets and living things, an odyssey spanning the galaxy and billions of years. And that journey continues. After you, your atoms will return to the environment, through respiration, through eventual decomposition, through the great cycle that connects all living things to each other and to the planet and to the cosmos beyond. Those atoms will be cycled through other organisms, other geological processes, perhaps eventually, billions of years from now when the sun dies, scattered back into space, available for incorporation into new stellar systems, continuing their journey through the cosmos. So when Webb detects carbon monoxide in Cassiopeia A, it's documenting one moment in the endless cycle of cosmic recycling, one instance of molecular formation in the aftermath of stellar death, one example of how the universe maintains its chemical richness through repeated cycles of creation and destruction and recreation. Rest now, knowing that you're part of that cycle, that your atoms are veterans of cosmic history, that you're temporarily assembled from material that's been through stars and supernovae and nebulae, material that will continue its journey long after you, participating in the universe's endless transformation of matter and energy into new forms and new structures. Cassiopeia. A shines in Webb's infrared images, its filaments glowing, its molecules emitting, its story of stellar death and chemical enrichment, written in the light that reaches us across 11,000 light years. And somewhere in that expanding remnant, carbon and oxygen atoms are meeting, bonding, forming CO molecules that will eventually be destroyed and reformed, and continue the cycle that makes complexity possible, that enriches the galaxy, that makes planets and life and consciousness possible. The supernova's violence created beauty. Its destruction enabled creation. Its death scattered life-giving elements through space. And the cycle continues, endless and patient, building the universe's chemical richness one stellar death at a time, one molecular formation at a time, one cycle at a time. And so we come to the end of our journey through James Webb's greatest discoveries so far. Though really, there's no end to what the telescope continues to reveal. Even as you've been listening, new observations are being taken, new data is being analyzed, new discoveries are waiting to be announced. The universe doesn't stop being interesting just because we've finished talking about it for tonight. We've traveled together across billions of light years and billions of years of cosmic history. We've seen the deepest images ever taken, revealing thousands of ancient galaxies from cosmic dawn. We've witnessed stars being born in stellar nurseries like the cosmic cliffs and L1527's hourglass. We found the most distant galaxy ever observed, JD's GS C14-0, shining when the universe was barely 290 million years old. We've detected oxygen in that same ancient galaxy, evidence that stellar alchemy began almost immediately in cosmic history. We've mapped weather patterns on alien worlds hundreds of light years away, detected specific molecules in exoplanet atmospheres, found quartz crystal clouds floating in infernal skies. We've discovered mysterious little red dots and puzzling jumbos that challenge our categories and force us to revise our theories. We've confirmed that the universe is expanding faster than our models predict, creating a tension that demands new physics to resolve. And we've seen carbon monoxide molecules forming in the violent aftermath of a supernova, participating in the eternal cycle of cosmic recycling that connects stars and planets and life across billions of years. 20 discoveries, each remarkable in its own right, each teaching us something about how the universe works, how structure forms, how complexity emerges from simplicity. And these are just highlights. Webb has made hundreds of discoveries, revealed thousands of objects, captured countless images that are advancing our understanding across all areas of astronomy. But here's what strikes me most about Webb's discoveries. They remind us that the universe is knowable. Despite its vastness, despite the impossibly large distances and timescales involved, despite our seemingly insignificant position on a small planet orbiting an ordinary star in an unremarkable galaxy, despite all that, we can understand what's happening out there. We can decode the messages written in starlight, interpret the spectra, measure the properties of objects trillions of miles away, map weather on worlds we'll never visit, witness events that occurred billions of years before we existed. The universe doesn't hide its secrets out of spite or malice. It simply operates according to physical laws, and those laws are consistent, universal, understandable. Light carries information faithfully across any distance. Chemistry works the same everywhere. Gravity follows the same equations, whether you're on Earth or in a galaxy 13 billion light years away. And because of that consistency, that universality of physical law, we can learn about the entire cosmos from our small vantage point, gradually assembling a comprehensive picture of how everything works. And perhaps that's the most remarkable discovery of all. Not any single finding about galaxies or molecules or black holes, but the meta-discovery that the universe is comprehensible, that human minds can grasp cosmic processes, that consciousness arising on one small world can understand the history and workings of the entire cosmos. We are, quite literally, the universe understanding itself, cosmic matter organized in such a way that it can look outward and inward and comprehend its own origins and evolution. The James Webb Space Telescope is one tool in that grand project of understanding. One instrument among many that humanity has built to peer more deeply into reality, to see more clearly, to measure more precisely, to learn more completely. And it's doing its job beautifully, revealing the universe in unprecedented detail, raising new questions even as it answers old ones, showing us vistas we couldn't see before and phenomena we didn't predict. So sleep well tonight, knowing that the cosmos is vast and ancient and beautiful and strange, filled with wonders we're only beginning to explore. The galaxies shine in the darkness, patient and distant, waiting for curious minds to observe them and learn from them. The stars continue their cycles of birth and death, enriching the universe with heavy elements, creating the conditions for complexity. The planets circle their stars, atmospheres circulating, chemistry proceeding, each world unique, each one a variation on the theme of how matter organizes itself in the presence of starlight and gravity. And somewhere, perhaps, on worlds we haven't yet discovered around stars we haven't yet observed carefully, other beings might be looking up at their own skies, wondering if they're alone, building their own telescopes, making their own discoveries, learning their own versions of the cosmic story we're piecing together. Or perhaps we are alone, the only conscious observers, the only beings capable of appreciating the universe's beauty and comprehending its workings. Either way, whether companioned or solitary in the cosmos, we're here, we're observing, we're learning, we're participating in the great project of understanding. Thank you for joining me tonight on this journey through Webb's discoveries. May your dreams be as vast and peaceful as the dark between the stars, as wonder-filled as ancient galaxies glimpsed across billions of years, as serene as the patient unfolding of cosmic history. The universe continues without pause, creating and destroying and transforming, following its laws, exploring its possibilities, building its structures. And tomorrow, if you wish, we can explore more of it together. For now, though, rest, close your eyes. Let the day's concerns drift away like stars fading into dawn. The cosmos will still be here when you wake, still filled with mysteries and wonders, still waiting to be explored, still offering its patient lessons to anyone willing to look up and wonder. Good night.